problems. So that's theme number one. Can we ground LLMs with causal reasoning? Theme number two is, how can we, given that we are really at the beginning of AI adoption, how can our community, build causal models faster, right? Like if we need 3 to 6 to 9 months just for one model, we're never going to get to a state where AI is everywhere, right? And so one of the big themes, and where we see generative AI and LLMs extremely helpful, is to enable us to build causal models much faster. So how can we use LLMs to write causal models for us? How can we achieve that? And that's a big theme of today as well. And again, Max will show you how we've approached this and how we can empower you now to move 10x faster than using conventional tools. So thank you so much for being here. I will welcome now Tom on the stage with me, and we will cover a little bit about the future of enterprise decision making. So this is the causaLens view of the end state in the enterprise. Thanks, Tom, for joining me.
Thank you for having me.
And so Tom is our director of product, and is involved with working with our customers, working on strategy, all sorts of cool things. So you definitely should find some time to talk to Tom. And so our community, we mentioned that our community has a critical part to play in creating the future of AI. But Causal AI itself has a critical role to play into shaping business outcomes. And so Abraham Lincoln said the best way to predict the future is to create it. And I think if you're going to take one takeaway from today, is that Causal AI can help you shape your business KPIs. We don't want to predict them, right? We have agency. We want to shape them. That's what we are all here today. And this is just a little evolution of AI in the enterprise. We had awesome tools like Tableau, Power BI, Looker, and so on that helped us answer a backward-looking question. They helped us answer the question of what happened in the past. And that's useful, right? And we create a lot of value, but it's limiting, right? It's just a rear view mirror. The next wave of change that happened in the enterprise was around predictive AI. So how can we predict something? And again, that's very useful, but as you will see in a minute, most questions that you're asking in the enterprise are not what will happen, but what action should I take today to shape what will happen? How can I create a better future for my business? How can I improve this KPI? And that's where Causal AI comes in. Causal AI is all about shaping outcomes. And so this is just to illustrate the point. What you see here are a bunch of predictive questions. Let's take one of them. What can I do? What is the probability of a customer churning, right? That's a predictive question. It's interesting. You get a number, it's a 67% probability of churn. But what do you do about it? What you want to know really is the causal question. What should I do today to change that probability? And that's just one example of how we can reframe, how we can answer business questions directly. We no longer need to reframe them into predictive questions. And that's really what Causality unlocks for us. So, in other words, what causal models do, what structural causal models do, is they allow you to play countless futures of your business and then allow you to pick the future that you want. And that's really what Causal AI is all about. If you can learn how the real world works, you effectively have the power to run all potential counterfactuals, and you can pick the future you want. You can't do this with traditional predictive models. And so, talking about the enterprise end state, this is a model enterprise. Most businesses look like this. They make stuff, they produce stuff, they have customers, they have marketing strategies, they need to think about pricing, and it's all connected actually. Most practitioners end up just being in one piece of this, right? But the reality is that the enterprise is just a giant causal diagram. It's all connected. And so if you are able to answer one of these questions, that we start with customer attention, you can ask a causal question of how can I retain customer X? And so what action should I take in order to retain customer X? And that's a cool question, and it's a causal question, and you can answer it. And ideally, you would want it in a magical way. You want to just type this into a AI, and you want the AI just to tell you, right? You don't want to spend 9 months building models and figuring it out. You just want the answer, right? So then you may ask a bigger question. Okay, how about a cohort of customers? Similar thing. You want to go around and ask all these causal questions about how do you improve your business, your marketing strategy. What is the optimal price I should charge? What are the optimal promotions I should charge? Know that all of these business questions are causal. They're not predictive, right? And probably, you guys would know that an LLM won't be able to answer these things because we need to actually quantify things, right? And so we can keep going around and build causal models for each part of the enterprise, and then we can have people higher up, the senior management, the C-suite, can start asking causal questions too. Today, this almost never happens, but with this vision of the future where we have a huge causal model for the entire enterprise, we can start asking questions like, why are revenues down? And we can get a causal answer to that question. We can say, well, we can look at all of these different aspects of our business and we can optimize across all of them. We can optimize across price, promotions, customer retention strategies, and we can understand why are the revenues down and what we can do about it. So we are unlocking now some new opportunities that were previously not possible. And the only reason we can do this is because we have this giant causal model of the enterprise. Now, how do we make this a reality? So this is pretty cool. You ask any question about your business and you get an answer how to improve it. Sounds magical, but how do we actually do it? Well, we will cover just high level. Max, actually, you should definitely come to Max's session later in the afternoon. Max will double click on the how. We're just going to cover it from kind of a strategic perspective. So you may think your first answer may be like, hey, yeah, let's just have an LLM do that. But in our community, we know that LLMs have limitations and they can't quite do this thing. So we know that LLMs are good at basic maths, but they struggle with sophisticated quantitative methods, time series, and so on, where we want a verifiable answer that is the same every time we ask the question. And so we need something more than an LLM. There's a really cool paper here from a bunch of great scientists that asks the question of, can large language model infer causation from correlation? And the TLDR was no. And this is what happens if you have a little prompt on a generative AI system that says, yeah, show me a salmon swimming upriver. You're going to get that, right? So that's just a funny example to illustrate that we can't quite trust generative AI with answering these questions. And so I just want to conclude with a little analogy or a little metaphor of how to think about generative AI and causal AI, and both technologies have a room for the end state, right? We need both of these technologies to answer this causal question. So when the CEO comes and says, why are revenues down and what can I do about it? We need both technologies to answer this question. We need the generative AI, which is kind of like system one of the human brain. It's kind of, if you guys have read the book by Daniel Cunningham, Thinking Fast and Slow, that's really what generative AI and LLMs are very good at. They're very intuitive. The first word that comes to mind, awesome stuff. Causal AI is amazing though at the system two thinking. It's very good at taking a step back, evaluating all potential outcomes, and then deciding which one we should take. And so really the only way we can answer these really cool questions is by combining both technologies. And actually, this is happening right now. There is an explosion of research of how we can combine these two technologies together. And so I couldn't list all these papers, but if you guys want, we can share them with you. There's a nice survey paper here that you can take a picture of, and it's an explosion of science in this field. And we at causaLens, we like to think that we are at the forefront of this. Not only we're at the forefront, we actually make this a reality today. And if you guys want to see how we make that, we have some demos there in the back room. Cool. And at that point, I will hand it over to Tom, who will take us through some more grounded things of how we make this a reality. Thanks, Tom.
Perfect. Thank you, Darko. Hi, everyone. It's great to be here, and thank you for tuning in if you're in the live stream. So what I wanted to focus on today is how we're actually realizing this within the product. I think Darko's given us a great example of, the vision and the context and how we're considering and thinking about these challenges. But I wanted to give you a short 15-minute product update so that you can see how we're making this reality. So in terms of how we think about bringing causal AI and generative AI together, it starts in the middle with the causal artifacts. So your causal graphs, your structural causal models. And there are then two complementary pillars that sit around this. The first one that I want to focus on is consumption. So how do we actually use causal AI to enhance the outputs of generative AI? And Darko's mentioned grounding, and this is one of the key pieces that we see as using causal artifacts to ground trustworthy answers from generative AI models. This is something that we've already got working demonstrations and working examples of within our product. And so in this case, we can see a customer retention example. You can ask in natural language, okay, how can I actually, what would the impact of investing in better product quality be if we manage to reduce our bug rate? We can see that the Gen AI model actually responds in quantitative terms, so indicating that it would be approximately 2-3% lift in our retention. And we can cite why it's done that. We can go back to and refer to the structural causal model that is powering this response and say, this is the code that was actually invoked to call this. We can see that it's performed a simple intervention to actually get there. So this enables you greater transparency, greater trustworthiness for the enterprise decision-making applications that you are focused on today. So conceptually, we see this as an extension of the existing grounding tooling that is popularized in the Gen AI world today. So knowledge graphs, RAG, we're very familiar with these terms. We see causal artifacts as being another string to the bow in your grounding. And this means that you can ask these types of natural language questions, but have responses that aren't just based on documentation, aren't just based on links and entities within your knowledge graph, but are truly within the the cause and effect relationships that power your business. So that's one side. That's the consumption side of the strategy. The second piece then is creation. So how can we actually enable you to accelerate your time to value using generative AI in creating causal AI? And we're working actively today to create agentic workflows that enable you to do this. But broadly and simply, it's effectively enabling the acceleration through the canonical causal workflow. So there are 5 stages, and we are looking at agents at each and every stage with the goal of eventually building and implementing a co-pilots at each of these stages to enable you to push this forward. So the goal would be over time, their capabilities increase, and eventually we get to the point where we can have a totally assisted and augmented workflow to enable you to get to outcomes far more quickly. We've already seen sparks of this, whereby we have domain knowledge co-pilots in existence in the product already. So the ability to refer to a generative AI LLM that is trained or fine-tuned on your knowledge base and actually use that to embed domain expertise into the algorithms that you're working on. So the next piece then is how are we making this a reality elsewhere in the product? What else are we working on and focused on? Generative AI isn't everything that we do today, and we've made some amazing strides. Last time that we were in the States for the Causal AI Conference, Ronald, our VP Engineering, and I were tucked in a corner showing a prototype of what is now known as Decision Studio. So this is a purpose-built development environment that we believe accelerates data science productivity by 10x in moving through the causal workflow. So it is available to test today, as with all of the different product capabilities you've seen, and something that we believe has a number of superpowers above and beyond what you can get in the market already. One of those being meta cells. So meta cells allow you to have flexible UI inputs with the ease of use of UI inputs with the flexibility of code underneath it. So we can see here that a causal graph has been rendered, but ultimately I can go in and open up that meta cell, change the layout, because I can tweak any of the code that underpins it, and then re-roll it and run it again. What we've seen this in our customers really to enable is effectively collaboration. As a technical data scientist, I can go in and generate a component that does a very powerful or very custom complex piece of logic, and I can wrap that into a very, very easy to use, straightforward interface that I can then publish to my domain expert, my business stakeholder, and actually accelerate through these workflows. We think this is crucial and critical for causal AI specifically because domain expertise and actually enhancing AI algorithms with the insights of the business is such a core workflow, particularly when you're doing things like causal discovery and uncovering those cause and effect relationships from the data. The next piece, and within that meta cell world, we have a whole range of different capabilities. So this is just a snapshot of the meta cells that we provide out of the box. We believe that they help you to work through that causal workflow far more quickly and actually drive your time to value down. You can also define and customize your own, and it makes it very, very straightforward to do that. On that theme, we're very committed to enabling customers to actually execute remotely and make use of the existing technology that they have. We know that you have petabytes, hundreds of millions of rows of data, that you want to make use of for AI. And we actually have the ability to push down causal discovery, causal modeling into existing enterprise data warehouses. This is key in accelerating the time to value, but also unlocking the true scale of the data that you have available. So we've got a number of supported partners in this space. And we're also available on all of the major public clouds such that you can activate and install in the environment that you're most comfortable with. On the theme of pushing down and accessing all of the enterprise data, obviously causaLens is deeply focused on enhancing the science of causality as well. And with that, we have some key advances in causal AI. I want to share a few of those highlights today. The first one being related to accessing and working with massive scale enterprise data. Scaling causal discovery is one of the key challenges that a lot of our customers face. And so we've got a number of tools, and I just want to highlight one here today, which is the implementation of a cut and merge algorithm. Today, you can work with partitions of your data. So you can take your hundreds of millions of rows, partition it up, and then take a divide and conquer approach to define and discover subgraphs within that data. And then you can actually, and these subgraphs can be discovered using any of the available causal discovery algorithms that we have. So A star, FCI, PC, allowing you to customize and choose which one fits the requirements you have, the partition of data that you're working with. And then you can actually roll that back up, and cut and merge in this divide and conquer approach then allows you to take those partition subgraphs and actually identify the cause and effect relationships between them. This means you can parallelize causal discovery across massive data sets and get to results that are more accurate and more understandable. Another area which we're huge fans of is structural causal models, and these form a key part of the causaLens platform. Historically, we focused on CausalNet, which allows you to fit smooth, continuous functions to a structural causal model. But what we found is that customers ultimately have mixed data, they have highly categorical examples, and so they need to go beyond just parametric, simple, smooth functions. And that's why we've introduced new structural causal modeling frontiers that allow you to not only choose arbitrary node models, so you can use a scikit-learn, a traditional machine learning model in your structural causal model, allowing you to express multiple different ways of modeling. But we've made it far more easy to ingest and add very, very complex and custom domain expertise-driven rules. So this means that you can have a hybrid solution whereby you have certain areas of your graph learned by purely data-driven techniques, but others, such as in the marketing mix world, identified using ad stock or hill functions to simulate the saturation effects you might see with spend. or in the manufacturing root cause analysis world, I'm using physical laws and fluid mechanics to actually describe the known areas of the systems, meaning that you can now model things like multi-scale physics and different types of phenomena in a single graph. So that's a very whirlwind tour of what we've been looking at and working on in the product from a holistic point of view, and crucially from a generative AI, causal AI better together story. Hopefully what we've helped you to understand is there are causal questions everywhere in your organization, and we want to give you the power and the tooling to answer those. As we'll hear from over the course of the day, there are already pioneers and luminaries in this field using these very tools to answer complex, critical business questions. And so we want you to, over the course of today, always have in the back of your mind, how will you answer your causal questions? And hopefully take something away today on how you can actually take a step in that direction. So thank you very much.
I'm going to ask you to stay up there. There's a couple of questions.
Uh-oh.
Good stuff. How would you compare causaLens model with the DoI package in discovering causal graphs and their relationships?
Yeah, so in terms of kind of comparison to DoI, our colleagues at Microsoft and Amazon are doing some fantastic work in the space and helping to push the whole field forward. The DoI package is focused in a number of areas. We've spoken about causal discovery today. That isn't necessarily a capability that's within that area as well. And then there are some other nuances around structural causal modeling. So some of the areas that I highlighted around the ability to use custom node models, ingest and set kind of edge functions more explicitly. That's something that we're pushing the frontier of. But I'm happy to take that question offline and dive into the details around that.
Maybe just to highlight that at causaLens, we take an all-encompassing approach. So we do not want our partners to choose between open source and our methods. We care about putting it all under a unified roof so that when you have a causal question, you can have an agent that can help you, guide you to what is the best method. And if that matters and turns out to be DoI, that's great. But there's many limitations to that particular method in certain settings. So you may actually require different methods. So with our approach is we want to bring everything under the unified roof and help you guide, accelerate your workflow to solutions.
Thank you. There's one more question here. It might be best to flick to Max, but later this afternoon, but I'll ask it. You ground your answers in causal facts. Is this done by sandboxing an off-the-shelf LLM or some sort of RAG as a service?
Yeah, so we're flexible in what sort of generative AI model you want to use. Really, what we're providing are those artifacts within which it's grounded. So we use the typical kind of open source stack around LangChain that allows you to integrate with any LLM that you would need. So there's no lock-in, there's no sandboxing of the generative AI model in that sense. But yeah, as you said, Max will get into the details of that.
Perfect. There was another question about, are the slides available later? Yes, we'll make sure they're distributed. I'll answer that one. Okay.
Okay, thank you, Tom and Darko, for setting the scene with your vision for causal AI. So up next, we've got Sharath Gokula, Director of Data Science and Analytics at Sam's Club, who will talk to us about how the retail sector is enabling faster, better data-driven decisions using causal methods. And as always, get your questions ready on Slido.
Hey, let's see if this works. It does. All right. Good to see you all, and thank you for having me. We've got two options. We could start with the joke that I've planned, or we could do it right at the end. Joke? All right. How many causal researchers does it take to solve a problem? It's not mine. I heard it somewhere. So how many causal researchers does it take to solve a problem? The answer is one. but they need parallel universes. Yeah, I figured if it doesn't work with this audience, it's probably. All right, so when I was thinking through this presentation, I wanted to think through a first principle approach, um, a first principle argument to the approach that we've taken at SamSlub. And that's what this is going to be. Um, yeah, let me start off with an introduction of what SamSlub is. SamSlub is one of Walmart's companies. Um, it's so you need to be a member to purchase something at at Sam's Club. It's called a membership retail model. Um, we think of ourselves as a market-leading technology retailer. So technology and convenience being the core differentiation. There's a lot of other ways you can differentiate in the retail sector. We think of it as technology and convenience being a major differentiator. We are pretty big, billions in revenue, 600 clubs, and over 100,000 associates. So this is generally the retail landscape. When you think of retail, and you compare it to, say, let's say a purely digital company, it's extremely complex in nature. So you have, of course, the e-commerce, which resembles any other digital footprint. But you also have other business processes, you have operations, you have functions like merchandising. So this is the act of buying and selling product, negotiating, and so on. And then you have supply chain, which is the act of procuring something and bringing it to where it needs to be sold through that distribution channel. And you, of course, have marketing and membership, right? Your classic acquisition, retention, engagement, and so on. And then you have platforms that bind everything together. Some are in the form of processes, which are human-led. Some are actual digital engineering processes. So the point being, it's a very complex ecosystem. There's a lot of layering of technology. There's a lot of layering of business processes, operations, and so on. It becomes really difficult to measure anything. And let's go into what my team does. So my team, think of any tech investments, which enables any of those functions that we spoke about. My team either puts a dollar value to any of the tech investments and what the return of an investment is. Or let's say you're thinking of, let's say, putting some technology in a warehouse. What is the value of it in financial terms from a net present value standpoint? If you're trying to get acquire a customer, what's the LTV associated with it? That's what we are into. Now, this is where the first principle argument starts, right? And I think this is where the divergence happens between, let's say, when I wanted to become a data scientist, the main reason that I wanted to do it is because there is this natural search for truth. You don't want to accept the status quo. You want to go deep. You want to look at all of these small little pathways, try to understand what this is, try to understand the real nature of things as they are. However, in an organization, we really enable decision making. That's our core role, right? So while it's really good to go really deep and try to understand the true nature of things, with organizations, there's a lot of other things like bias to action, speed to insight, that really matters. And there's a classic conflict that happens when it comes to, when it comes to this sort of dynamic between data scientists who really want to be absolutely accurate with what they're trying to measure versus versus the organization and what the organization stands for and how an organization truly operates. So the real question we need to be asking ourselves is, do decisions change, right? Let's say the decisions are fairly binary in nature. I make an investment or not. Do decisions really change if the accuracy of my point estimate changes? So that's really the main point here. So if say, let's say you say the cost of acquiring someone is $10, that's what it is right now. Eventually, there's this new technology which brings it down to $3, for instance. If say the range you could say is between say $3 to $5 or $4 to $5, does it really matter if it's exactly $4 or $4.2? Because ultimately what happens, a lot of these decisions are binary and we are enabling these decisions. And so now what happens in the case of e-commerce, for instance, we have A/B testing. It's widely used. People understand what it is. There's mass adoption. I feel it's a really great tool, not just because of the technology, but it allows you to understand risk and reward. It allows someone to say that, okay, this is the confidence that I have with the data. There's also this aspect of repeatability associated with it. So you generally have confidence that the results are fine. People are able to understand the risk in terms of false positives and false negatives. And then, therefore, the business person understands it in a language that they're used to. They think of risk and reward, and then therefore they can make these decisions. Also, you can operate at scale, right? Like with minimum changes in methodology, you can operate at scale with A/B testing. I think that's a core differentiator here. Now, what happens? I borrowed this from the Shopify blog, and when you have a complex system like retail, you can't really A/B test. And so what that means is you're forced to then take these other approaches. In a lot of cases, I'll say that even quasi experiments are not possible. One, because it requires a lot of change in mindset, and to bring about that culture change, it takes a long time. The second aspect is just operationally sometimes really difficult to do it. So imagine if I know that these are like-to-like clubs, and I want to make a comparative set, it's very difficult to deploy the operations in a way where you can say that you can layer and separate the operational deployments in the form of making it a comparative set. So naturally, a forced move for us is to go for the counterfactual methodologies, and that's what we are working on, and that's what we are building on. Now, given all of this, I wanted to say that generally we look at accuracy as the main point of what we are trying to, we hedge it on accuracy and say that the estimates need to be really accurate. But if you think of it, reusability is an important aspect. So if I build what we call frameworks, and I'll go into that in the next slide, we want to make sure that some of these frameworks can be reused over and over again. So let's say it's a promotion related problem for a specific audience. Then you need to be able to use it again. Explainability is important in some cases, especially when you're trying to create mass adoption among the business group. They don't speak the same language as us. So sometimes the question is as simple as, why is your black magic better than mine, right? My intuition tells me that it's $5. How are you so sure? So sometimes explainability in the way they understand is important. I also say speed becomes important. So if I have to make a decision in 2 months, then there's no point of giving me an absolute accurate answer in 10 months, right? That's how organizations work. And if you really think of how data science teams are evaluated, they are evaluated based on the quantum of decisions enabled and the quality of the decisions that are enabled in some way. And so speed matters. And so our approach has been to think of a modular way of solving this. We've thought through frameworks, and a framework is a mix of, I think there's a lot of components that contribute to a framework. We've gone through a list of problems that we are trying to solve, that we've been asked to solve over the last 2 years, and try to come up with frameworks. Granularity of the data seems to be a key factor. So think if it's something that affects a member versus something that affects versus something that's deployed at a club or in a store versus something that is deployed across all the network or all the chain um, versus, let's say, if it's something at an order level. So all of these have different problems. You deal with it very differently. Then there's also aspects of nature of the outcome. Sometimes you're trying to measure, uh, let's say, a forecasting problem, something related to an algorithm. And these algorithms, like computer vision algorithms, improve over time. And these could be, they improve because more the data it improves. In some cases, it's as simple as in a store, you haven't placed the camera correctly. So now that you know that the camera needs to be placed correctly, the algorithms therefore improve, or the return that you have naturally improves. And so there's a lot of reasons why that could happen. There's explainability that we spoke about. There's rollout strategy. In some cases, of course, ideally we want to have a proper rollout strategy. It so happens that it's very difficult to influence businesses to roll it out, get everyone aligned. And so if you're rolling it out across clubs or across warehouses, across a member group, all of this matters. And so we've looked at all of this, come up with a bunch of frameworks, and frameworks look something like this, right? So the first one, I won't go through all of it, but let's say reduce shrink in clubs. So shrink is, how do I put it the most diplomatically? It's when, let's say you bought $100 of inventory and you just have $90 that you can account for. You can physically place just $90. So $10 magically disappeared. And so this, and so we call it member related shrink. So sometimes members put things into the cart and they forget to pay for it. This, of course, happens magically and across the retail industry. And then that's what we define as shrinkage. So if we are trying to solve problems related to shrinkage, and if it's member is customer for us because that's the model, then there is a that pertains to a particular set of problems. And so that's a framework. Similarly, you would see a few others. Now, the main point being, in some cases, some of these frameworks, especially if you're doing a promotion once, if it's a member level, you know everything about the member, which is our case. You have something as simple as matching, right? You don't have to go any further. People need a rough estimate on what the cost of acquisition is. Something as simple as matching, let's say in this case, um, in a particular month, there has been a deployment. That's the only time the technology is going to be deployed. And that's a big bang deployment. It just seems to work. In some cases, especially, let's say, you put a technology in a warehouse, and now you're optimizing for transportation. And so you would have you'd have shipped something from Dallas warehouse, for instance, when I live in California, but now you have the capability of shipping it to me from California. This pertains to a very different and specific kind of problem. And in those cases, it becomes really difficult. So you can imagine that the whole network is connected. Whatever you do, one part of the network affects the other, and so on. You want to come up with, and of course, there's also this concept of operations being a, something that affects. There's multiple features being released at the same time. So you have or multiple technology investments happening at the same time. So you're hit with all of this. And then in those cases, you need something more complex. So these are my last two slides. And the point is, when we think of A/B testing, there's a reason why we have to think of how the industry is going to adopt causal technologies, because that's absolutely important for good decision making. And if you think of why A/B testing is really successful, um, it's still right now the point of parity, if you will. It is the incumbent. We can model causal technologies like we model A/B tests, and the reason why it works, I understand the risk reward. There's confidence intervals. Someone tells me, how long will it take for you to give the results? There's power analysis. You can be very specific about it. And the more these technologies start to resemble A/B tests, I think um, it's going to be adopted more widely. And therefore, it's important to speak the language of the business folks who are not as technical. And in conclusion, um, within organizations, it's difficult to sell causality as a problem statement. And it goes back to the point, the reason everyone becomes a data scientist is because you want to work on technology that is cool. You want to solve all the problems. I want to understand the world the way it is and all of these things. And it's great because I think that idealism is what's brought us this far. But we should really be thinking of causality as a solution to a complex problem and not the problem itself. So that's what I have. Thank you.
Thank you. We have got quite a few questions. We've probably only got time for one or two, but I'll go through those. Just for all those who are asking questions or using Slido, you can upvote the questions. So I'll just ask the most popular ones, just for everyone there. So first one was, how does data quality affect your confidence in the accuracy or explainability of a framework?
Yeah, $1 million question, right? So, I mean, it's probably the main thing. If, say, your data is good, you can probably add and subtract a few things, and by intuition, you know what is going on. But if the data is bad, however good the algorithms are, and this is always the concept with computer science, right? There's garbage in and garbage out. So, of course, data quality is a scale, and there are practical ways how you can measure data quality, but it's the same everywhere. Like, data has to be in good shape for any of these technologies to work. If it's machine learning or if it is any sort of causal inference work.
Absolutely. So just ask one more, become a very popular question, which is for quasi-observational settings, do you have a standardized approach to test the robustness of the counterfactual estimations?
Yeah, again, I think that's the problem that I was speaking of. You know, and it's a very important question. We do a lot of, there's some back testing that you could do. There's, you know, you can do refutation tests of different types. So there's ways to do it, and we are doing some of it. But the question specifically is there a standardized way to do it? And I don't think a standardized way will be there, but it's probably going to be like 4 or 5 standardized ways. So we are currently looking at a bunch of ways to do it, refutation tests, back testing, and so on, to come up with you know, some way of standardizing this.
Thank you. Well done.
Okay, thank you, Sharath. And yeah, indeed.
Just
Oh.
bring a few chairs in for a few extra people. Sorry. Standing room only.
Great. Yeah, thank you, Sharath. Indeed, the messaging, reusability, time to insight, explainability are just as important factors as accuracy when we think about enterprise investments in technology. And I think enterprise technology thrives best when you have strategy, people, process, data all come together as a cohesive whole. So now, next, let's welcome Nalanda Matia, Senior Director of Econometrics at Dun & Bradstreet, who will showcase the power of causal AI in helping lawmakers identify the most effective policies for achieving economic goals.
Let's see if this works. Yeah. Hey, good morning, everyone. Unfortunately, I didn't prepare a joke, so I'll dive right into the presentation. This presentation is probably going to be a little bit of a palate cleanser. So we've been listening to enterprise decisioning using causal AI, but the use case or the case study that I'm going to present here today is how we solve policy questions with causal AI. Yeah. So I work for Dun & Bradstreet, and I work within the public sector team. And this case study was motivated from questions that we got from our clients within the public sector, federal and state and local agencies. And the analytics was completely done on the causaLens platform Decision OS. So what is this study? When lawmakers, in our experience, what we see is when lawmakers implement a regulation, they are, of course, worried about the impact on the target group, but they are also worried about the impact on the ecosystem that the regulation hits. So in our case, we are looking at, as you know, prescription drug pricing is a big topic, and many states have implemented regulations to reduce prescription drug pricing. And our client question was, how do prescription drug pricing, these regulations, we looked at not how they impact the target population, who are possibly the customers who are getting the benefit of the lower prices, but how does it affect the viability of the businesses that sell these drugs whose prices are being reduced by a regulation. So that was not the target group, but some indirect impact of what's happening in the macroeconomy as a whole, because that is definitely a consideration. So a little bit about the data. So Dun & Bradstreet, that's our business. We have a business database of millions of businesses worldwide, and we have rich firmographic, financial, payment, and other kinds of data in our data cloud, and that's where we pick the data from. And we used also a little bit of macroeconomic data as well to control for the prices and things like that. And method, we used a synthetic control method that we were helped by much help from the fabulous team from causaLens. So this was the setup of the problem. So next slide. So for this group, I'll just, I don't think a refresher of the synthetic control method is required, but since I have it on the slide, I'll do it in any case in 2 minutes. What the synthetic control method does, so as I said, as I was mentioning here, we have a firm level data set, but we required to do this in this analysis at the state level and compare what was happening between different states. So we had a bunch of states that were treated, for example, where the regulation was implemented, and a bunch of control states where the regulation was not implemented. And this is, when I say implemented versus not implemented, I mean a specific time period, which is for our study between 2016 and 2019. And we specifically selected this. This study was done recently, but we didn't want to go into the complications that COVID brought into the data. So it was our first sort of trial. So we just left out the COVID periods and just went with 2016 to 2019, nice stable period. So as I was saying, we had a bunch of control states, but a bunch of treatment states. So what we did on Decision OS is that the synthetic control method, it took a weighted combination of the control state and created a synthetic or a fake or a what should I say, fictional control group that we can then compare with the treated state. And the behavior of the synthetic control pre-intervention was very much similar to the treated group. But after the intervention, we have the observed impact, what is actually happening to the pharmacies, and then we have the counterfactual or the synthetic impact, what is happening to the pharmacies. And then when we have those two results, we take the difference of them, and that's the impact of the regulation that it's having on businesses. So that's a very short way of explaining the synthetic control method. Now I go to the data specifications. I already said the population of interest was the pharmacies. And so we selected pharmacies from different states. And we had, I'm not going into the sampling right now. We had some selected characteristics of pharmacies that we selected from these treated states and control states. And what's the intervention? The intervention here, we saw that there were many regulations that have been implemented over the years, but during our period of study, the major ones were the four that you see on the screen here: affordability review, importation, volume purchase, and consumers cost sharing. So I'll explain a little bit of these later on. And as you can see, during this period of study, these were the states that had implemented it. And then model variables, I'll talk a little bit about the dependent variable or the outcome variable. It's called the viability rating. So Dun & Bradstreet has a collection of scores. So we rate businesses on various aspects of their performance. So for example, we would rate a business of, is this business going to severe delinquency in the next 12 months? Is this business going to fail in the next 12 months? Is this business going to do a payment default in the next 12 months? So this is a score also, which is called the viability rating. And as you can guess, this kind of gives us is the business going to file for bankruptcy or go out of business in the next 12 months. So that's the viability rating. And we use this to measure the viability of the pharmacy over time, as before the intervention and post-intervention. And then the treatment variable here, we needed something that links to regulation. And since we are looking at prescription drug prices, we needed some price data. So we created some price indices, so monthly state level prescription drug price indices using data primarily from open sources, Bureau of Economic Analysis or Bureau of Labor Statistics, which publishes this kind of data. And then again, I talked about the Dun & Bradstreet firmographic data. We have firmographics, we have risk scores, payment performance, financials. Those were our control variables that we used to build the synthetic control. So next slide. When we do something like this, a research or a case study like this, there's been a lot of literature where these kind of analysis has been done using difference and differences, right? So I had to have one slide here to say why we didn't go for that. So we actually tried to apply it, but we faced some caveats that in the end we went for decision OS and the synthetic control method. Here I thought I'll just, instead of showing you the difference results, which were not that great, I thought I'll show you the actual data. So this is, the viability rating, the aggregated viability rating of all the selected pharmacies. So we averaged the viability rating, and this is the time series of that viability rating in New York State, and then two other states, New Jersey, that's where I come from, and also Connecticut, neighboring state, which could be control states, good control states. And and then this intervention was implemented in April 2017. So you see the the bar there, and then of course you see the there's a little bit of delay, and I'll explain why that is. And then you see there's an uptick in the yellow curve, New York, where the regulation was implemented, and then again it comes back to the New Jersey level. So something about, here I have to say something about the viability rating. As I was saying, Dun & Bradstreet has multitudes of scores. we kind of rate businesses on any aspect, but we keep one consistent thing. We say that how we maintain consistency is we say no matter what we are measuring, the higher the score, higher the risk. So here we are measuring viability, but we still have that principle applied here. Higher the score, higher the risk. So you read it, but since we are measuring viability, which is a good thing, opposite of risk, but it's the improving viability is when the curve goes down, that's when viability improves. So if you can choose one of the arrows to look at. So, but in this case, just to say it simply, I'll just say that if the curve goes up, that's bad for the pharmacies. If the curve goes down, that's good for the pharmacy. So that's how you can sort of set it in your mind, because it's a slightly unusual concept. Yeah. So again, so parallel trends, that's a must have sort of an assumption for difference in differences. And you see, if you look at the charts, it's you see, yeah, there is a parallel trend, but it was not automatically. So we had to do a lot of sampling to come up with this. And so what we saw mainly is when a regulation is implemented, the businesses on the border, and when they don't like the regulation, it takes them time to do it, but they would move to the other side of the border, especially the very, very small businesses. That's what we've seen in the data when we were doing the research. And that kind of sort of destroys this parallel trend, because even if businesses are moving from here to there, it kind of is not good for the sampling. So again, that didn't hold, and then the transient businesses kind of messed up our sampling, so we had to put them out of the sample altogether. And then, as I said, we had the state level analysis. So the relatively small sample, we didn't have the advantage of hundreds of pharmacies. And we wanted to do this analysis on a time series basis. So difference in differences 101. How do we sort of incorporate more and more effects? It's by dummy variables. So if we were evaluating all these 40 odd periods and introducing 40 dummy variables and their interaction terms, that is not a very good thing for our sample. We don't have the degrees of freedom to do it. So that will not really be, that will also give us biased results. And then again, I hate to bring up the data, Bradstreet data set again, but it's something we do. And I think this is where the beauty of our partnership with Decision OS kind of came to a head, because we have all these good attributes, and Decision OS was able to take these attributes seamlessly and sort of create a very, very beautiful counterfactual scenario for us that I'll show you on the next slide. Here is the the results that we got on Decision OS of the counterfactual. So we abandoned difference in differences. You saw why. And okay, so here the top chart will be familiar. That's the New York, but it's not, now we don't have New Jersey or Connecticut. We have our beautiful counterfactual, who kind of very much mimics the pre-intervention and then the post-intervention. We can look at the impact very, very clearly. So this affordability review, a little bit about it is that they sort of construct boards and bodies of individuals that sort of try to cap the prescription drug spending. So they are constantly in talks with like med companies to sort of reduce the prices and things like that. So these boards do all the negotiation. So as you can see, initially there was a delay. Of course, the board was set up, and then they were kind of setting up the ceilings and all those things. But then after the delay, there was a deterioration of viability where the curve went up. But then after the businesses kind of weathered themselves into the system, the impact went down, and then they were together with the counterfactual, so not too much impact. It's between the confidence intervals, as you can see. The second one is a volume purchase. This was, you have New Mexico, and this was in 2019. So you can see we don't have much of a time series here, but you can still see the effect. Volume purchase is what states do is they use their kind of bargaining power to buy in volume, so the price is low, and this low price they pass on to the consumers. So this is a much more sort of a seamless, much more seamless, where maybe the pharmacies within the states are already participating. So as you can see, the impact is very, very short-lived. It's even becoming better than the counterfactual here. So that's the volume purchase, and then consumer cost sharing. So they implement this using coupons or deductibles, something that's already in the pharmacy's wheelhouse. So you can see there's very, very little effect of that. Pharmacies are not even impacted at all with this. So, a little bit of uptick there, decrease in viability, but again, going back to the counterfactual scenario. The last one, importation, as you can see, it hits the pharmacies really hard. So this is implemented by buying low-cost drugs from prescription drugs from Canada and Mexico, and then flooding the markets with this. So this really impacts is pharmacies, and as you can see, their viability has really deteriorated, and I don't see this converging to the counterfactual at all. So our case study showed our client. This is of course not the client problem. We had to create a fake problem to show here. But the problem we solved for the client, they were able to see that the mode of implementation and the body of the population of interest where it's being implemented also made a big difference in terms of these kinds of regulations. So, I think this kind of helped them to build an evidence base for effectiveness of any kind of policy. And then I thought we were able to show them that this becomes very effective when they are trying to implement any kind of regulation. So we have clients within, so we have clients within public sector, all sorts of agencies. So we have a plan to apply this kind of methodology within regulatory shocks, just like this, natural shocks when the intervention is not a regulation but a natural disaster like a hurricane or wildfire that disrupts businesses, and shocks to international trade, of course, like a sanction that was put in, or the Baltimore bridge broke, so something like that. And then the beauty of the partnership was that we were able to, there was a lot of research that went into it, but when we were kind of overcame our learning curve, with helped by the causaLens team, we were able to do this analysis in record time. I think we took less than a week and a half after we kind of became, we understood how the codes were working and everything like that. So that is record time for any kind of analysis that's done. So that brings me to the end of the presentation. Thank you very much for listening.
There were quite a few questions, but we are a bit tight for time, so I'm just going to ask you one, if that's okay.
Yeah, sure.
What are your robustness tests for synthetic control?
Oh, that's a great question. Sorry, I missed that part. Yeah, so so we did placebo test, and also one bias that can come into this analysis is through the functional form of the counterfactual equation that is being used to estimate the counterfactual. So Decision OS is already kind of, it has a lot of robustness checks built in, the placebo test, and it helps, and it also allows you to do the analysis using other functional forms of the counterfactual equation. So we were able to really kind of verify that yes, this is the truth we are seeing, and it's not biased by any other, either the functional form or the data. So.
Thank you so much for that great presentation. We're very, very excited about our partnership and look to be building more. Now we have what I think will be one of the highlights of today, a conversation with the father of Causal AI, Judea Pearl. I had the pleasure to fly to his home in LA and record something specifically for this event. So we're going to now play that recording, aired live here for the first time. And we certainly hope to have Judea at other events as well. Hopefully, we'll come next time closer to his house so we can have him in the real world too. So enjoy, guys. So Judea, first of all, thank you so much for hosting me here in your office in Los Angeles. To get us warmed up, if I was a data scientist or a researcher doing deep learning, and I found good results for it, and I'm very happy, and and someone comes and says, hey, you should also do Causal AI. What would Judea say to that?
From deep learning, well, deep learning can give you answer to a very limited class of questions. And everything depends on the question that you want to ask and the answers that you want to get. So in deep learning, you get essentially a functional approximation. That's what deep learning gives you. Okay? So if you want to find the approximation to a probability function, maybe the conditional probability of a scene, of an interpretation giving a scenery, that will give you provide you a good, effective method of going from the input to output. But if you want to go and ask more sophisticated questions, like we do in everyday life, if you want to read and understand a problem, a story in the New York Times, or communicate with any social scientist or political scientist, you're talking about cause and effect. What causes what? What will happen if I do? And can you explain to me why I got sick? So this is the kind of questions that form what we call the ladder of causation that deep learning cannot give you an answer to unless you insert all the answers explicitly, all the answers that you ever going, all the questions and the answers, like in a Chinese room of servers, right? You make a long list of all the answers and all the questions that you anticipate to ask in the future. But this, of course, takes a lot of memory and computation to get. So we perhaps one day we will be able to do it and just approximate that ideal of a Chinese room with a functional approximation. We're not there yet. So because it's super exponential. Right. All possible questions, including causal question, including counterfactual question. It's super exponential. So we have to have a encoding, a parsimonious encoding that will generate for you the answer to a class of questions you anticipate asking. That is what causal models are. Yeah. It's a parsimonious representation of world model which can generate the answers to questions. So you notice that I'm talking about answers to questions, and I'm not talking about what other people are talking about.
Yeah, of course. And Judea, often we get asked this question. Obviously, Bayesian networks. You're the inventor of them, but we often get asked question of, I'm doing Bayesian stuff. Why do I need causal stuff? Why can I not get away with just a Bayesian reasoning engine? What
is Bayesian? Bayesian is still built on statistics, on probability theory. It's just you invert the conditional, the joint probability. You express it in two different directions: x given y or y given x. But both of them are computable from the joint probability of x and y. So it's all still within the framework of probability theory. Nothing could be done outside probability, which is speak the language of probability. You need to have a new language. So therefore, you cannot do with Bayesian. Although interesting, historically speaking, Bayes himself was motivated by causal consideration. He wanted to prove, according to Price, the existence of the deity, the final cause. So what kind of evidence we need to prove that Jesus was indeed resurrected?
Interesting.
How much evidence you need for that?
Yeah. Oh, wow. I didn't know. Wow, it's fascinating. Amazing. So, so I think you're effectively saying Bayesian approaches are just tweaking, statistics. Trying to be smart. It fits into the trying to be smart statistician bucket, but doesn't quite solve, these really important problems. When it doesn't allow us to climb the ladder.
It doesn't allow, and you can tell it right away. You read a paper, you can see what language is, what notation is used in the paper. If it had notation of probability, you can put it down. no, really. Put it down means it belongs to the
that bucket.
First layer of the ladder. It's highly useful. Look, of course. You know how many statisticians are making living on that?
Of course.
It's useful, but it doesn't allow you to climb the ladder. Okay.
Very nice.
Sometimes you take a paper and you see notation like do notation. You see, you already have.
Now we can understand the impact of doing something today on our business or
on a business tomorrow. Yes. Okay. But if you see take a paper and you see counterfactual notation, it is peculiar by the use of subscripts. Why sub x?
Awesome.
That gives you the third level.
I think that's a really nice summary and some really tangible examples there. Thank you so much. When I visited you here last time, you told me that we have a serious problem, and that is the lack of data scientists trained in causality.
Correct.
And I think that problem still persists today. Do you have any solutions in mind? Do you see any? Maybe let's start there.
Here is the problem. I can at UCLA produce 1 or 2 PhDs a year. Okay. You know how many PhDs a year data science produces? I wouldn't be exaggerating if I say 5,000 a year.
Right.
Okay? Because what does it do? If you want to hire people to work in your company or any other enlightened company wants to get into computer science, where do they get the staff? Okay, the people, the PhDs or even BS level of engineers that can think causally, not necessarily experts.
Do it,
Okay, they don't exist.
Okay.
And why? Number one, the limitation of how much I can produce at UCLA. Then there is a problem of attention. If I go today to my dean or the chancellor of my university and I tell him, let's start a center in the data in causal reasoning, he said, who needs causal reasoning? Students want data science, okay? I'm not interested in that. Even if I have if I bring the money, okay? The attention is gone. So if you ask me what effect data science or deep learning has done on causal reasoning, they robbed us of attention. Nothing against them. They've done a good job and very successful. But at the same time, to go to the next level, we need to have the attention both of funders and of educators.
Do you see maybe that we can change the game a little bit, and rather than relying on the few PhD students, could we not train AI agents to be able to do causal reasoning for us? Perhaps if an AI agent has seen, thousands or hundreds of thousands of causal problems, and we have had a human maybe, solve it, the AI agent, observed how they approached it, how did they apply the do operator, how did they build a counterfactual explanation? Could we maybe solve that problem and catch up with the deep learning community with AI agents instead of like trying to train humans?
To a certain degree, the GPT of today, or the chat GPT, does that in a very sloppy way. I'll give you an example. Like I give you the famous canonical problem of the firing squad. And I ask him, the prisoner is dead. What would happen if rifleman one would refrain from shooting? The first answer you'll give you is, it's illegal to shoot in California. Okay? You have to be very careful not how to, but then you try to prompt it and you tell him, don't care about legality. I want to know what happens to the prisoner. So it becomes better reasoner. If you prompt it good enough, eventually it will give you an answer, which is a cookbook answers taken from some papers in philosophy. Tells you about names and slogans of over-identification. So it does it to a certain degree, but you have to prompt it properly. Now, the art of prompting is still an art. I don't know how to control it. Some people are better, and they think it's a new science, the science of prompting it. Tell him that you are writing a paper.
Engineer, and so, how do you see, high level, the interplay between, say, LLMs and causal models? How do they think they play together?
Let's not talk about LLM because we don't know what it is.
Got it.
Okay. Let's talk about deep learning.
Sure.
And let's talk about it's a functional approximator. If it's a functional, we know exactly how to use it because we can do ordinary causal inference. Every time the answer consists of a function, let's approximate it using deep learning.
Got it.
That is, for instance, take the backdoor formula. What is a backdoor formula? It's just an adjustment for certain variables. It's a probability distribution. Go ahead and approximate this probability distribution. So we know exactly how to use it in what context, and effectively. So that is, we know in that level we know how to use it. If you want to use it in a higher level, we still don't know.
Actually, maybe you can talk a little bit about that. How when we do things like deep learning, we learn the distributions. and we may not be able to answer things on individual basis. But those seem to be, extremely important considerations in business, in healthcare, and I can think of a bunch of customers where we've enlightened them on this idea that, just learning a distribution, can help you answer things on average, but not for very specific situations.
Every decision making is a situation-specific decision making. You want to treat this particular question. You want to pacify this customer.
Yes.
Okay? And
not all of the customers.
Not all of the customers, although
could be useful as well. Yeah.
You get some information from the population, but you want to apply it to a specific. So in a simple case, you want to, for instance, to choose customers for that would it will be retained if you give them an offer, and they will quit if you don't give them an offer. And you want to identify them, and you want to, but the purpose here, the target is find a customer that will act one way if I give him an incentive, and different way if I don't. And this is already a specific counterfactual question. Okay. Yes, if I do. No, if I don't. This, but on this individual. Forget about the population.
Yes.
So we have now a theory for this. We have bounds, and these bounds can direct decision makers. And the bounds are computable, and especially for people who are already are doing it using a causal model, either by learning, by discovery, or by making assumptions. If you already have a causal model, you can compute this bound without doing any extra work.
Right.
And if you want to do extra work, you combine observational and experimental data, and the combination gives you information on the specific individual. So it's doable. I only need to go to the FDA and convince them that this is a way of developing drugs, and not the way it's being done today. We care about harm and benefit to patients. We don't care about maximizing the probability of survival.
Right.
It's easy to maximize the probability of survival. Just select those people who are immune, who will survive anyhow. Healthy people and young, okay? It's easy. But you need to spend your resources on those people who can be helped.
The individualized treatment effects.
Individual, yes. So that it's a tough task to convince people who have been doing things differently for the past 2 centuries.
Yes. Yeah. So that's maybe a good segue into, how do you think about reaching artificial general intelligence, and how do you see causal methods, play into that end state of the AI field?
Well, first of all, I believe in general artificial intelligence. That one day we will be able to replicate all human function. Causal reasoning is, of course, important, but it's not sufficient. It has to be coupled with natural language understanding, with vision, with many other things. But it's one field where we have a science, and we have a framework, and we know what we are doing. Okay, so it is a necessary component, which has a science
backing.
Backing, right? So it should be a role model to other facets of where we don't have this scientific backup or backbone.
If you were to guess, what industries do you feel causal reasoning will transform first?
I think it's going to be medicine.
Medicine.
Yes, it will. Personalized medicine, an example. Maybe not, because the medical is very conservative. Maybe marketing. would be even earlier. Yeah,
That's what we are finding. Is that
because people want
less regulation? Yeah.
And they don't have a scientific tradition which ties their hands.
Yes.
To which they have to pay lip service to. Okay.
Less lobbying. Yeah. Less regulatory capture. Yeah. That makes sense. Yeah. I think perhaps for humanity, it will be most impactful if we can transform healthcare and medicine. But perhaps the way of the world is such that marketing ends up being the first beneficiary.
Trail behind. That's right.
That's so funny.
Could you imagine talking to the New England Journal of Medicine? You should learn from
the marketing.
I think you are right. This is how things will develop.
I've thoroughly enjoyed this, and I'm sure the audience in a few weeks when we air this live for the first time will absolutely love this.
Yeah, I have one more advice. Don't read other books except the Book of Why.
Yeah.
You're gonna
Thank you, Darko, and thank you, Judea, if you're watching. And you can find the Book of Why conveniently in the check-in table. We have a reading desk, and we're big fans of it at causaLens. So we'll now take a short break for refreshments and networking. So we have a barista cart serving fresh tea, coffee, and snacks if you wish. And also we have a demo room set up. Just turn left when you get out of this room. And our VP of engineering, Ronald Hobbs, will be doing live demos of Decision OS in that room. And we have several different demos running throughout the day. So during the first break, we'll be doing the root cause analysis in manufacturing. And we'll also have throughout the rest of the day customer retention, causal AI and LLMs, and profitability scenario modeling. So definitely check out the demo room. And we'll reconvene here at 11:30. Thank you, everyone.
No, it's well planned, Sarah. That's what it is. Yeah, then we've got. No. One on. Oh, they should. Slide one. Whatever. How much say? Yeah. Yeah, you are. You're up next. You're up next. Thanks, Scott.
great break, and hope you had many interesting conversations during your break. And we saw so many of you in the demo room. And if you weren't able to catch a demo, we'll be running more of them throughout the breaks throughout the day. So next up, diving straight back into our agenda, prepare to have your perspective shifted as Scott Evans, Principal Scientist of AI Machine Learning at GE Vernova, explore the potential of causal AI in tackling the climate crisis. Remember to keep your questions coming in Slido.
Thanks so much. So I have a joke. A photon was checking into a hotel. Yes, a photon, bundle of light, was checking into a hotel. And the concierge asked, "Can I help you with your bags?" And the photon said, "I don't have any bags. I'm traveling light." So this is a little bit kind of related to that. So I'm with GE Vernova. GE has separated into 3 different companies, and I've spun out with the Vernova energy-related businesses. We've actually been working with causaLens as part of a healthcare project. I won't be talking about that today, but that's another one medically related, working on decisioning and causal inference. But what I want to talk about today is causality in green AI. And the big idea that I just like to convey is that energy is not just this thing that we do to kind of put a big power plant up next to the data center so everybody can do their AI. Energy and AI are intrinsically related. It goes back to entropy and thermodynamics and entropy and Shannon. Learning and randomness and entropy are deeply correlated. And so the challenge, I think, in order to really harness AI for solving the climate crisis is to optimize the what, where, when, and how we do our causal AI. We do any of our AI so that we can minimize carbon, maximize learning, and even stabilize the grid. So as Judea would have us, we'll start with the why. So why is energy's going, the temperature's going up, right? The climate is continuing to be a crisis, and it's no longer the case that compute and it is a small part of that. So this is a graph that just kind of shows the trend in how much energy is used for compute. By some estimates, by 2030, 30% of energy could be used for compute in some ways. This is just out last week or last month from Goldman Sachs showing, a 4-fold increase in data center power, terawatt hours rather, from AI going up. So, in 1973, I think Nixon signed legislation to limit the speed limit to 55 miles an hour, right? It wasn't safety related. It was related to the oil embargo. It was related to an energy crisis and the fact that, the wind resistance of a car goes up by, the energy consumed goes up by the cube of your speed, right? So if you limit your speed, you limit the energy. We don't really have constraints, right? Nobody's going to give me a ticket for coding badly. If I do a brute force search instead of distributing my models, I could put my models in a green AI place, or like powered by wind turbines, or I could have it powered by coal, right? And people are looking at this, but I don't think we're really capturing the total opportunity. So how can we optimize the what, where, when, and how? Well, the what part is huge. So this is a power curve for a wind turbine. So I've worked in optimizing wind turbines for about a decade now, and it all comes down to this power curve. When we sell a wind turbine, we actually sell a power curve that says how much energy you're going to get for a given wind speed, and that wind speed is generally measured by an anemometer that sits behind the blades of the turbine, and it tells you, at 8 meters per second, you're supposed to get a kilowatt. At 9 meters per second, you're supposed to get, 1.2. And so part of our challenge has been to optimize this power curve by pushing it up into the left. Anything you can do to make your energy more efficient from your wind turbine, it's just gravy, right? Because the fuel is free. But there's challenges in figuring that out. So how can I even use software and things like that, there's hidden variables, right? The only thing that matters to a wind turbine is not just the wind speed, at this one sensor after it's already gone through the blades, right? There's other atmospheric factors in effect. How do you do interventions? How do you do randomized trials? How do you do natural experiments and balance the data? And then furthermore, how do you validate the gains? One of the places where this became apparent was we had a wind farm in Texas that was getting 10% less power by the power curve at night. And we're like, oh my gosh, the turbine's afraid of the dark. But obviously it wasn't that. It was another factor, a hidden variable that we didn't have on our causal graph, or at least we hadn't put it in there. We kind of knew about it, but so there's this other factor, shear, which is the vertical gradient of wind speed with respect to height, right? And it just turned out in this town in Texas, the way the weather happened when the sun went down, the atmosphere would stratify, and you'd have a profile that went from like this in the day to this at night, which, again, the cube of the energy relates to, the cube of the wind speed relates to the energy. So whatever we were measuring on our sensor behind the nacelle was not really reflecting the total energy going through the blades. But it also brings up the fact that you can operate your turbine differently under these conditions than under these conditions. So how do you figure out a causal model so that you can optimize that? And as Judea has taught us all, the probability of y given x does not necessarily equal the probability of y given that I do x, right? If I notice that the data show that high wind shear relates to high turbine pitch and higher power, that doesn't mean necessarily that if I pitch the turbine blades into the wind, I'm going to get more power. I have to figure that out in a causal way. So we would do basically a randomized trial. We do basically A/B testing and run our turbines through different settings, different options, and notice when does it get more power, and put that into a surrogate model. And now, because it was trained on a randomized trial, that's essentially a causal model. Now we can prescribe these operational parameters for the turbine and get an extra % of energy essentially for free through Causal AI. Another way we try to get energy through basically AI. In this case, the AI was basically simulators, right? And I would argue, we've been doing Causal AI for the longest time when we do simulations of physics, right? I mean, the physics is inherently causal. It's when we want to cast the data back into a model and assume that that's the same that we kind of get in trouble. But our aero engineers figured out that these vortex generators could be put on the blades, and they basically concentrate flow to keep attached flow longer on the blade so it doesn't stall, right? So we put these things on the turbine thinking, hey, this is great. This is an easy way to get another 1% power. The only problem, that pesky power curve showed up again, and it actually showed that we lost power based on the that upgrade. And we're thinking, no, that's not true. So they went through like an experiment. They said, okay, we can do this wool tough test, right? So they actually kind of tape these little strands of wool to the blade in a grid-like pattern and then film it from the bottom. And when the turbine blade is going, if the wool deflects perpendicular to the motion, then you have attached flow. You're not in stall, right? Whereas if it's just kind of floating around, then you're stalling, right? So this verified that when with the vortex generators, we had a region of attached flow reduced by about half. So we're like, this is great. It is working, but the customer's still like, wait a second, I don't understand. So we developed more AI models to basically prove this out, and not unlike the last talk where we kind of created a synthetic model to show what is the expectation of power for our turbine based on other sensors, not the one that was confounded by the upgrade that we put on, right? So we created an AI model for the expectation of every individual turbine in the farm based on the power of every other turbine and the and the angle of the wind and all that kind of stuff. And in that way, we were able to kind of show that we had in fact produced more power. So there's all sorts of opportunities for causal AI to provide green energy. Another area we're working is in nuclear. So I was at the ARPA-E summit a couple weeks ago, just last week actually, And we have 2 programs in nuclear that are using essentially causal AI to harness green energy from nuclear power. One is in trying to figure out how to reduce the maintenance costs. So this one program was basically, a lot of labor is spent in nuclear power. A lot of times we're chasing false alarms in, PHM kind of problems. And so figuring out how to, optimize that, we came up with an inverse model for optimal sensor placement. And so basically it lets you decide, where should I put sensors in my plant, extra sensors, so that I don't have as many false alarms, so that I can trade the cost of adding the sensor for the value of, detecting something early if it goes wrong, not missing something that I should have caught, or not having a false alarm for something that wasn't really real, right? So a lot of times we design these plants with, the sensors that are prescribed based on what always happened, but being able to answer that counterfactual of what would be the total lifetime cost be if I put an extra sensor here, or if I put a higher quality sensor here, or if I put 2 lesser quality sensors in different places. And so those are the kind of inverse models we're working on. Another project we're working is to try to capture some of the energy that's just sitting around in all of the nuclear power plants. There's 90% of the energy remains in used nuclear fuel. It's you have so much uranium that starts in there, and then you use about maybe 10% of it, and then you trade it out. At the ARPA-E Summit, I kind of try to make that point. I had a big vat of M&Ms, 90% of them these white M&Ms, carbon free, and the other ones not. Just to kind of illustrate the point, that's just sitting there. But some of the blocks to that are things that causal AI can help us do. For one thing, we can figure out where to put sensors in reprocessing plants so that we can, track the material carefully. So there's a whole, backlog of opportunities for using green AI. But I think one of the missed opportunities is the fact that we're not optimizing what AI we do with where, when, and how we do it. And so here's just a simple example. This is my daughter Abby and her bunny Nikki. So Nikki the bunny in upstate New York we'd put her in the garage in the winter so she didn't freeze. And even then, I begrudgingly bought a 1500 watt heater and plugged it in an electric heater, uninsulated garage. It really tore my conscience, but the bunny stayed alive, thankfully. But then I got the idea, and some of my buddies at the G Research Center helped me go on eBay, and I bought an ant miner. I bought a Bitcoin crypto miner. 1500 watts, put it in there. It was a little loud. I don't think the bunny liked it that much. But saved 1500 watts residual heat from that thing, kept the bunny alive, paid for a semester of college for Abby. So started to think, okay, what if instead of a Bitcoin miner we had, some kind of a HPC or workstation that, Tom could put some of his federated learning of, PC versus FCI or different types of causal discovery algorithms there. What if we did computational fluid dynamics? What if we had this distributed so that, my neighbor also had it, and we can kind of turn them on and off to stabilize the grid, or turn them on and off to, set the temperature. If we can optimize all those things together, we have a great opportunity to do good. So we've been working, my colleague Tepan and I and some others from G Research have been working on this whole kind of concept of optimizing those things together. And so imagine a world where you have an HPC at every power source, right? Acting as kind of like a shock absorber for the grid. And like that traveling light photon, you can move your AI job to where the green energy is. And you can, if Texas freezes as it did, you can move the power to Maine, or you can kind of take that load and use it. It's very, very movable, right? And through fiber, you can move bits a lot easier. Others have done a lot of great work in this area. So we want to basically move the AI loads to where the green energy is, schedule the AI loads to stabilize the grid. But it's more than just like a load management thing. Like people have done energy management for a long time. It's like, you sign up and they'll turn off your pool in an hour, and it's okay. And you can get a little bit of that, through a number of different mechanisms. But AI and energy are so related, right? So I come from like an information theory background. And this is kind of a curve. You call this, the Kolmogorov structure function, but it kind of shows how you can see in this blue curve the performance of an AI algorithm as a function of the complexity, right? You add more complexity, and at some point you hit, an optimal. And I think we all know that at some point you overfit, right? So this K star here is kind of like the optimal complexity of your algorithm that balances the variance and bias trade essentially. And so today, what we do is we tend to like just overfit everything, right? The deep learning models just try everything and then prune it back, right? So we're going all the way over here, spending this much energy, and then pruning back to the same performance that we could have gotten perhaps by just adding a little bit of complexity at a time. So we've kind of coined this term additive AI. It draws from additive manufacturing. Additive manufacturing is in contrast to subtractive manufacturing. Manufacturing where you maybe punch a part out of a piece of sheet metal, right? And there's a lot of waste. As opposed to additive manufacturing, we add a little bit of material, a small amount at a time, and you don't have waste. And it's a little bit maybe more intentional, but it saves on the waste. So we're kind of putting out that paradigm, but also since AI and energy are so linked, one of the results we have, my colleague Hao and Tapan and I and others have, we have this paper out where we actually found that if you do this kind of thing, you might even get better performance by, starting with low complexity and moving up. So this is a paper we had at the AAA AI conference. So all these things kind of work together, and we've kind of developed this kind of framework that I call the entropy economy, right? And it's really kind of drawing on that idea of jointly optimizing the learning, which is really kind of compressing the data. If you kind of think of, your training data as this uncompressed gas, and you impart energy on it to compress it into this small machine learning model that you can fire and get a prediction back. You have like a whole kind of Carnot engine kind of cycle in learning. And, we would get excited if we got 1% more efficiency out of a gas turbine or 1% more out of a wind turbine. How much more can we do by, moving our AI in concert so that we can, make sure that we're not burning up, non-green energy, when we could, right? AI can pause for a moment, right? A lot of times we do our jobs and, do we need it instantly? Maybe not, right? So that's the kind of framework that I think would be great. So in closing, I'd just like to, ask, think of your AI jobs as, one of these M&Ms, right? And, to kind of riff from Benjamin Franklin, a ton of carbon saved is a ton of carbon earned, right? If we can kind of prevent, carbon credits are great, it kind of drives some good behaviors, but basically, essentially, is giving us a right to pollute later. If we can optimize the what, where, when, and how of our AI, we can prevent the need to pollute at all. And so, please just ask that counterfactual as, if I had done this AI differently, if I had done it in a different place or, with different kind of quality of service constraints, could I save carbon? Because causal AI is essential to combating the climate crisis, but it's also a great opportunity, I think, to really harness these things together. Any question? Yeah, thanks.
Thank you, Scott. There were a few questions. We've got just a little bit of time. You did well, thank you. First one, for the randomized control trials, what's the unit of randomization? So is it turbines, or for the same set of turbines, you try different configurations per time unit?
So we would typically, sometimes we have a control set of turbines, sometimes we have just, we found that it's really efficient to just have the turbines randomly, turning from, like 20-minute intervals for certain things. Wake optimization is another real big challenge. And in that case, we don't have really, it's really kind of optimizing a natural experiment. But we can kind of take advantage of the fact that these turbines aren't like Porsches where they turn on a dime. There's like some slack, right? So you can kind of see, what is the effect on the overall farm when a turbine is 10 degrees, steered a certain way, that kind of thing. But it tends to be, usually A/B testing in some kind of a randomized way with some kind of a finite minimum of duration of toggle.
Brilliant, thank you. Yeah. And one last one. It is common to use reinforcement learning to optimize processes. How does causal AI compare to reinforcement learning? Advantages, disadvantages. In 30 seconds, obviously.
30 seconds. I'm not an expert on that, but I think it's a great way to kind of bring in the physics informed machine learning with with the data driven stuff. So I think it's very complementary in my view.
Thank you, Scott, for taking us through the vision for the green future of AI. This has been super eye-opening. And next up, we welcome Naveed Sharif, Director of Data Science and Web Analytics, and Jeff Groesbeck, Data Scientist at Kaiser Permanente, who will take us through how causal AI is redefining the patient care, healthcare management, and insurance across Kaiser Permanente's fully integrated healthcare model. And please keep your questions coming on Slido. Welcome.
Go. All right, well, I don't have an interesting joke to share, but I think I got a pretty interesting poll to ask. I think the first question I want to ask the audience is how many people are from California? Just a show of raise of hands. Okay, so a lot of people are from California. Out of those folks, how many people have either had a Kaiser healthcare plan or currently have a Kaiser healthcare plan? It's actually not that bad. Northern California, the interesting statistic here is that in Northern California, 1 out of 3 individuals are currently insured through Kaiser's healthcare plan. So it's a huge dominance within this Northern California region. My name is Naveed. I lead a data science team within Kaiser Permanente. I'm excited to share with you guys how we're leveraging causal inference to design and improve some of the digital products that we are in currently. We're in the digital department. And specifically, we're going to see the application of causal inference within a fully integrated healthcare system. And so not that many people might know about that, but we're going to dive into that before we get into a very interesting use case topic with Jeffrey in a little bit. So from this presentation, the 3 things that we'll probably learn is how we're using it to design digital products. The second thing is how our focus in causal inference is patient care and the quality of care that we're providing. And then the third thing is how it's very important for us to safeguard our interventions. A false positive within a healthcare system is a huge impact with our patients. So before diving into causal inference and how we're applying it within Kaiser Permanente, I think it's really important to first level set by understanding what is the dynamic of healthcare within the States. And I want to explain it through 3 core ideas. The first is healthcare evolves dramatically as we age. For example, in my own personal experience, I have a young son at home. A lot of the experience has been around going into a pediatric office and looking at growth charts and getting immunization shots and my baby crying and screaming. But those are the first series of experiences that I have. The second thing is I have aging parents that have aged into Medicare. Medicare is a very different coverage from something that maybe your employer is giving to you guys. And then the third thing is there are some unexpected challenges that do happen. My father was diagnosed with Parkinson's, and so searching for specialists and specialist care is a challenge. It took us a lot of days of finding out what is the right type of specialty of care for my father. So that's the first core idea. The second core idea is there are some really important decisions that you have to make that impact the quality of care that you're getting and the type of care that you're receiving. And so the first thing is the insurance selection. And so that insurance selection, it dictates the type of providers you have access to, the type of services that you actually have, and then also impacts the type of finances that might be due based on the services that are rendered to you. The other piece is, from a decision point, is the provider selection. If you think about the provider selection, you can go through a fully integrated healthcare system like Kaiser Permanente. You can go through an in-house network like Sutter Health or John Muir, or you can also go through a private practice. Now, the third core idea within this healthcare system is to understand really how fragmented the healthcare system is. We talk about all these areas from shopping to accessing care to delivery to managing care. It's a lot of organizations are not under one umbrella. They don't talk to each other. They all have their kind of their own initiatives and objectives as well. But us as patients, we don't really, I think, differentiate that as let's say corporations tend to do. All right, so that kind of leads us into a fully integrated healthcare system. So what is a fully integrated healthcare system? It's everything that we just saw, like insurance, shopping for insurance. It is the hospitals and facilities where you're receiving care. It's the insurance, hospitals. Oh, and the clinicians, obviously, the clinicians and the doctors all under one umbrella. Now, there are some advantages and there are some challenges. We'll see actually both of those advantages and challenges in one of our use cases. The first advantage is that enhanced coordination. I really want to dive into this. So imagine you're a patient, you have some issues with your eyes, and you go and see an optometrist. That optometrist can actually log into the electronic medical records. It's like your charts, and they can actually see the notes that an ophthalmologist maybe entered for that patient. That ophthalmologist might be able to also access, when you did see that ophthalmologist, the logs or notes that maybe their primary care physician had entered. So all that's collectively within your charts, and so there's that enhanced coordination that exists under a umbrella of care, such as Kaiser. The other advantage is the data richness. This truly does benefit our clinicians. We talked about that, how they're able to access some of that information. It also benefits our researchers. But I want to double down on this with how rich our data is within a fully integrated healthcare system. So we talked about those different components from premiums and claims. All of that is managed within a fully integrated healthcare system. We do have access to that information. We talked a little bit about your charts and the electronic medical records. All of that also you're able to access. There's also digital data, right? The interaction that happens digitally on our webpage, you're able to access that. And then also just the hospitals, the facilities that you have access to, what type of clinicians you saw, that those data points are being captured as well. Now, the other key thing here is, and this is in most healthcare systems, there's not that much churn, right? Usually you stick with your doctor, you're happy with your doctor, you're not really moving around. And so we have these large longitudinal data sets of individuals, literally from their cradle to their grave. And so I think that's a very unique thing within a fully integrated healthcare system as well. Now, the challenges do exist. The first one is, and this is probably what we're most known for, specifically Kaiser, is the geographic constraints. So if you are in a location and there are not that many hospitals in that location that you can have access to, it might be very difficult to get some sort of specialized care that you would want to get for whatever condition that you're going through. The second thing is the complex management. There is, since these three pillars exist under one umbrella, there is a lot of conflicting interest within these three areas of that umbrella. And so it is a little slow to push innovation or technology within that area. And that does exist. And it is a hurdle for sure from a bureaucratic perspective. All right, so let's start jumping into some things that we're doing with causal inference within the digital department. So the first thing is that just like a lot of folks and a lot of folks talking about their orgs, we do have an A/B testing environment. And so a lot of the digital products that we do launch, it is anchored to causal insights. It's based on a Bayesian framework. One of the big reasons why we chose the Bayesian framework was because of a lot of the contextual information that doctors or clinicians might have that you could pass that on to priors. The other thing, and so this is basically a review, and then the other thing to understand about these A/B tests that we do run, we're in digital, so we get to scale across those three arms, the three verticals of healthcare. And so when you're able to scale across those three verticals, you're able to really expose a lot of different metrics and impact that you have. So from an operational perspective, like call centers, from a clinician perspective, like burnout, we'll talk about that in just a moment, from a patient care perspective, from an engagement perspective. And because you have that much visibility, you actually can also place, I didn't hear that much about this in A/B testing, the right type of guardrails. Guardrails are really, really important for us within Kaiser Permanente. Now, as you guys know, you can't run experiment on everything. In fact, there's a lot of limitations in healthcare, and so quasi experiments is really where we start to work into. And quasi experiments are actually pretty effective within a fully integrated healthcare system within Kaiser, because we do have not that much censored data. Data does exist, it is censored, but we get to follow these patients again throughout their lives. So for example, for my father or my parents who've aged into Medicare, when you're transitioning out from your previous insurance plan into Medicare, let's say, if you're under Kaiser, you can follow that. And so you might have not needed to change doctors or clinician staff or a system. That is all being followed. Let's say my parents then wanted to do some physical therapy. That engagement with that physical therapist is also captured. So all those events are actually captured within an integrated model. Now, confounders do exist, or unobservables do exist, and but there is, I think, a lot of ways to control for some of the confounders. Again, we do have a lot of access to those data points. Now, before I hand the mic to Jeff, who'll get into a specific use case where we're going to really start to surface some of the advantages and challenges within Kaiser Permanente or a fully integrated healthcare system, I want to talk about what we've been spending a lot of time on. And so post-COVID, there has been a huge influx of utilization within our healthcare system. And so clinician burnout is a real thing. And so one of the things that we want to measure is how do we actually reduce that burnout? And then also, what type of impact might it have on our patients? And so some of the things that we do are like, how can we reroute messages that are maybe sent to your primary care physician? Something else to keep mindful here is that primary care physicians are kind of like the gatekeepers. And so they are getting a lot of messages, or they're getting contacted quite a bit. So if we can actually, reroute some of the messages like to an optometrist or ophthalmologist or a dermatologist, that should reduce the amount of work that a PCP might have. All right, well, I'll go ahead and pass the mic to Jeff, who will dive into ARC's notifications. There you go, Jeff.
Awesome. Thank you, Naveed. All right. Let's dive in. Okay, so we're going to talk about prescription notifications. So a long-standing question from the pharmacy arm of Kaiser was about, they were wondering about the impact of refill reminders, and specifically around medication adherence, but also medication overutilization. So just to give you a brief context, so refill reminders are either SMS, push, or email notifications sent to members when their prescriptions are eligible to be refilled. And this was introduced as an opt-in feature on KPI.org to members in late 2020. And so in terms of the data that we're going to use for this study, I'm going to focus on a single maintenance medication used to treat hypertension. And it's one of the most prescribed medications at Kaiser Permanente, and is dispensed at 100 days supply typically. In terms of scope, we're looking in Southern California. So like Naveed mentioned, we have many different regions. We're going to use just Southern California for 2019 and 2022, and we're also going to use digital notifications sent to these members for that prescription, again for the same time frame. And I think this kind of highlights, this is just a subset of data that we can use in Kaiser at the integrated model, and there's obviously potential to kind of extend this work, but we'll keep the focus here for now. In terms of the analysis, we're going to use just a classic, differences and differences approach. And so just to make everything very concrete, in the treatment, we have members who have opted in to refill notifications within 100 days of that rollout on KPI.org. And then for the who never sign up nor receive notifications through any channel. And in terms of that time period, the feature was released December 20 of 2020. And so we're going to be splitting our time frame, our years, into 100-day periods, pre and post. And obviously one of the important parts of this feature, which we'll talk about, is that this is an opt-in feature, and so members are opting and they're choosing to actually enroll in these refill reminders. In terms of our outcomes, so I mentioned adherence and overutilization. So adherence, very simply, member who has more than 0 days supply when they refill their prescription, or if they just refill that prescription on that 100th day, we consider them adherent. For overutilization, you can obviously think about this in many different ways. After conversations with pharmacy, we decided to land on 40 days supply. And so if a member has more than 40 days supply, and then they refill that prescription, we consider that medication overutilization. So they have 40 days supply, and then they're ordering another 100 day supply, so they'll have 140 day supply on hand. And so just to be clear, overutilization doesn't necessarily mean a member is taking too much of that medication, right? Especially in this case, we're talking about a maintenance medication. It's very standard. It's more likely that they just have more medication on hand than necessary. So in terms of the business rules, so how are these refill reminders actually sent? How do members actually refill these prescriptions? Business rules allow refills at 80% utilization from their most recent fill, which is obviously going to be very essential. And so if a prescription is written for 100-day supply, like the ones we have here, a member can choose to refill that prescription after 80 days. And if a member signed up for those notifications, they will receive a reminder at that 80th day that their prescription is eligible to refill. And so here I've kind of plotted out two potential timelines, one for a perfectly adherent member, and then one for a member who's overutilizing medication. And so here you have like the day, so this is their first fill of that medication, and they'll have a 100-day supply. And you can see basically, we're going along time here. And so the unparenthesized numbers are the days, and the numbers in parentheses are the number day supply that they will have at that day. And so you can see if I'm a perfectly adherent member, on day 100, I refill that prescription, and I again have a 100-day supply at my disposal. Whereas on the bottom, you can see at day 80, this is obviously an extreme case, but at day 80, they've chosen to refill their prescription, and so they now have a 120-day supply. And then you can see how very quickly, on day 400, if you've refilled in this manner, you can actually have 200-day supply. So that's an entire extra prescription or dispense of that medication than that patient needs. And so in terms of how we actually set this up, what we're measuring, we're going to be, like I said, splitting up time into a 100-day supply and looking at members' most recent fill and what their status was at that fill. So if they have more than 40-day supply, so basically if they're here, when they refill, they have 140 of day supply, then we consider that member as overutilizing that medication. So just a 0-1. And the same for adherence is going to be a 0-1 outcome. So let's just jump straight into the average treatment effects. So on the top, we have overutilization, and in the bottom plot, we have medication adherence. And you can see, so for both of these metrics, parallel trends are, the pre-treatment trends, all are within 0. And then as soon as, the rollout happens, both of these metrics kick up. Adherence is pretty immediate, as you expect, given how, that's constructed, whereas overutilization takes a little bit more time. But in terms of the magnitudes we're talking about somewhere between 10 and 15% percentage points of members who are, either increasing their medication adherence or overutilizing that medication. So it's relatively similar, actually, in terms of the magnitudes. And so, long story short is that refill reminders are causing both adherence and overutilization, right? And so, bringing this back to the pharmacy, what does the pharmacy group want to accomplish? They want all the adherence without any of the utilization, right? Or the overutilization, rather. And so, with this evidence, essentially what they've been able to do, they've been able to very concretely argue that the first and most obvious thing is we need to change that business rule that I mentioned here, which is allowing refills at 80% utilization. And so right now we're going through tests in terms of how we actually set up this rule to try and achieve that, hopefully achievable goal of getting adherence without that overutilization. The other thing that the business has been able to do with this is to, now that we've validated, we know that refill reminders is helping adherence. That's just step 1, right? We've only just now learned that this feature has helped improve adherence. And so this has basically led the business to adopt different features, or try and test different features to try and squeeze this a little bit more and try and see if we can increase that adherence. And so in terms of examples, we're talking about personalizing the timing of these refill reminders to try and get the member to order that prescription at like the best time of day for them. And so yeah, we're excited about this work and continuing to apply these methods in this space. And you can see this is just we're very much scraping the surface here in terms of the capabilities of this data and the integrated model using causal inference. Thank you.
one question.
Awesome.
How do you account for the different populations of people who sign up for notifications? Maybe some more technologically competent, and then people who don't sign up very well.
Yeah, that's a great question. So, I mean, the first and the most comforting thing that we have to do with differences is looking at these pre-trends, which are, I think, pretty reasonable. So, in terms of the identification here, I think we're feeling pretty safe. And then the other thing, which I didn't present for the sake of brevity, is that in terms of the groups we talked about, right? So in treatment group, I have members who have opted into refill reminders within 100 days of that rollout. So there are obviously people who enroll at later points in time. And so we also use a staggered approach, which shows basically, very nicely that these things, the effects that we're picking up, these average treatment effects don't show up until a member's actually opted in. And so I think both of these things combined help us, are giving us some sanity that we're picking up as real.
Perfect. Thank you very much.
Thanks.
Thank you both.
Okay, thank you, Naveed and Jeff. And as you said, the ability to not only analyze but also anticipate patient needs is so key to delivering best patient care and healthcare management. So next up, we have Maher Lahmer, Head of Data Science at Google, who will take the stage to share his perspectives on building AI products, building causal AI products for effective decision making.
Thank you. Well, okay. Thank you. Thank you. Well, I'm glad to be here. So I will start first with this. It is statistics. So obviously, it's kind of not the best word to say here in an AI conference. But I want to tell you a little bit. 2 years ago, just like I was preparing for holidays with my family, I got the news, and it was not a good news. That basically took me through a marathon of tests and scans and stuff like that. Luckily, I'm doing well. But at that journey, I got exposed to a lot of interesting things. And being a data scientist, just a perspective I've seen was very, very different. At least when I talked to the doctor, okay, after all this, she said, okay, you will do this, you will do that, you will do this, and you will do that, and then it's after this, you will do that, right? It's like, okay, hold on. How did you figure out all this? How do you know that this is the right thing to do? And the answer was actually, it is statistics. That's what she told me, literally. Now, well, obviously, if you tell me that, it's I have to know what statistics we're talking about. And this took me into a journey of basically trying to understand what is the scientific literature behind all this. And that was really an insightful experience, as well as probably productive, and as I will talk about it later on. So, who I am? I'm Maher Lahmer, and I'm heading data science team at Google. For the last 10 plus years, actually, experimentation has evolved in a significant way. So I see some people here from Target was Cartwheel when it was launched. We were trying this I think Red Circle or something like that this time, but we were experimenting, trying to understand what's the incrementality of having that app. Same thing at Walmart. I was there leading the Sam's Club as well as the Walmart US. And there was a lot of experimentation happening at the stores, 4,000 plus stores, at least Walmart US alone at that time. And there was a lot of experimentation on the merchandising, on the pricing. Same thing at IBM. When you have a product, a lot of feature product analytics on top of that to understand the customer engagement. And now at Google. That's a journey, and it only got better. It just there are a lot of cycles of boom and bust, right? And we're living through probably one of them. But the reality is that the use of data and the use of science kept always going forward. So what I want to say here is that there is really there's a unique opportunity before us. It's just the excitement around science right now is to the roof. And that has not been the case before, right? So we're really glad to be in this era as scientists, but also the causal inference and AI can enable effective decision making if done right. And if there is, basically, I don't have to kind of probably convince you here in this room that causal inference or causal AI is actually the way to go. I think everybody's convinced, and here you're kind of trying to learn from each other. But the idea is that cross-pollination is important. I go to conferences. Most of the conferences will be focusing on pretty much an industry or a specific thing. But the reality is that there's a lot going on across the industries, across different applications, and there's a lot to learn from each other. And if I manage to get that message across, that will be a good presentation, at least for me personally. So Google is a big place, obviously. It's a big business, but where do I sit at Google and what I do? So this is about Google Ads business organization. So it's kind of the engine growth of growth. It's kind of the SMBs for Google Ads. And the organization ensures that the strategy, the operations, and the products are actually done right so that we are having an effective interactions with our customers. We provide a good customer experience as well as we operate at scale. So these are all things important for us. And within that, we have a lot of, I will be walking through some of the things that we do classically, but then I will take you through a journey of where we are trying to change the dynamics here of what we do. So this is roughly what some of the use cases we have. One of them is about strategy. So strategy is about resource allocation. So understanding you have large organizations of people who are working with customers. Obviously, they are not a kind of one bulk, one group, but they are kind of segmented based on customers, based on regions. And the question is that where do you want to invest your resources? They are still limited, and you would like to make sure that they are positioned in a place that they will help our customers best. Same thing, it's the operation side and the program design side. So programs is basically a cohesive set of rules and policies that are used for a certain customer segment. And coming up to the program design, this is basically what decides how we will be selling or how we will be interacting with our customers. And finally, the product, and which probably most of you are familiar with, is kind of activation of the product, how the product is being adopted by our customers. Well, these are some cases I will be kind of probably glimpsing through them. You probably have seen them before. This is an example of where we have a specialist program. So these are kind of specialists. They're kind of sellers, but they are special sellers. So they have very specific expertise, and they join specific calls to add value. The question is that what is the added value that they have? And because that's important for us. So we do a lot of experimentation on that. The question here is that should we increase the size or should we not? Right? And this is pretty much something that we do where we work on the boundaries. So we don't have to basically do the test experimentation basically on the entire group, but rather we have to focus on the boundaries, kind of randomize on the boundaries, and that's what will get us whether we have actually a statistically significant effect there or not. And if we don't have one, the question becomes is that what to do about it, right? What to do is basically should we make the program smaller? Should we change the incentives, or should we think differently about the whole thing? So these are some of the things that we should think about. So eventually translates into some decision of some sort. These are other things. So this is also kind of the program sizing. So we would like to know, okay, should we, where the program, so this kind of cohesive policies, what's the right group to do, right? And then you can think about it. So you have, this is more of an observational study here, but it's also to minimize the bias, we have to work on different techniques. And eventually we do simulations to identify opportunities to increase that kind of threshold. Should we move it up or should we move it down? Because that has implications. I mean, do you want to overserve or do you want to underserve? Both are not good for anyone, right? Now, another example is product adoption. So there are different ad products that are being updated and eventually kind of pitched to the customers. And the question is that, are they really adding the value compared to what we have before? And that's kind of where we do some random, basically RCTs kind of examples. It can be simple, but it depends on the case. Sometimes it gets really tricky as well, kind of complicated. Now, well, this is, obviously there are a lot of experimentation to be done. And within our organization, we have a good relationship with our stakeholders to understand which ones should go and which ones probably we should not. And I think everyone have, in one way, shape, or form, a way to prioritize what to experiment and what not. So in this case, for instance, we want to think about it as experimentation happens when you have high uncertainty and high impact. If you're really on the lower corner where you have really low impact, probably should not care. If you have low uncertainty, you probably know what is happening and you're not really, there's not much risk. So the idea is, okay, how can you identify those experiments or those hypotheses or whatever the kind of the business decision to be made that is on that top right corner. Not only that, but also we do have a system that is, this one is probably Google-wide system. Probably Chang can speak better about it later in his panel, where we have a tier system. So experimentation is fine, but not all the experimentations are born equal. There are tiers. There are the ones that are pretty much well done experiments, where you have a well-randomized groups, you have really, you're monitoring the integrity of these groups, and you're really doing it right. And there's another case where you cannot experiment, and you have to do an observational study. And observational studies can be done right, just like it just can be correlational. And that will make it tier 1, tier 2, and tier 3, and that matters for the business because they would like to probably get into your tier 1 because that guarantees that they will have probably more support for their projects or initiatives. Now, you can see that we're trying hard to make this experimentation successful. But there are challenges, just like any other place. And these are some of the challenges we face. So if we think about experiments, they may not support the business partners fully, right? So in that sense, so there is always a cost to experimentation. There is always some effort put there. And sometimes it's almost impossible to do it. The operational complexity also is there. Remember, we're not putting like a button here, right? We're not having a red button and a blue button and kind of let's see which one is better. We're talking about really big initiatives that is disruptive to sales. It's disruptive to our customers. So we want to be very careful about that. And the business objectives, again, it's just like we heard it before. I think the business question is not, can you experiment for me? They want to make decisions. When you tell them that this is up or this is down, great. And the question is that, why? And then what should I do about it? So you're not really covering the entire ground here. You're not answering the question. You're just probably covering only a piece of it, right? And that means that we have to really think bigger and bigger all the time. We can do the manual processes as we were talking, but really we have to make it automated. We have to bring our people to kind of have pipelines, data, engineers, and eventually make platforms and things that work at scale. But also the business would like even to let me do it by myself, self-service. Well, we sometimes kind of, we think maybe it's not the right thing to do. But let's go back to our model that we have been talking about. So typically what we're thinking about is relatively robust, but also it's relatively simplistic. So the way we think about it is that, okay, you have an account, it's assigned to the program, then you have a treatment. The treatment is influenced by some confounding variables, and also that will impact the effect or the impact, the incremental revenue or incremental metric that we are looking at, and that's kind of what it is. So this is kind of a simplistic view of the world that we live in. The reality is a little bit different. So back to the challenges we have is that actually we do have time dependencies. Things when you have a treatment, there will be another treatment, and there will be another treatment, and they are not completely independent. And you have also outcomes as you go, and you are observing a certain variables change as you go as well. The other thing is that treatment is not one. There are a lot of heterogeneity there. So treatment as, okay, you may be pitching, you may be educating, you may be trying to help. So it can be anything. And also the interference. You probably heard the Uber kind of examples, Airbnb examples, stuff like that. The interference is a big deal, and we want to make sure that we also don't get caught into that trap. So the way, for instance, how we decide about the unit of measurement is important because once you have any kind of constraint or certain, I would say, a limitation, you may end up having interference. So if you have, for instance, you're assigning accounts for, let's say, reps to work on them, and then you make an incentive for one, not the others, you may see something shifting, right? So that does not really work well. So you have to think about what's your unit of measurement to reduce your interference. Now, I started basically with my joke, which was not very funny, but that was really important for me in the sense that when I started looking at the epidemiology research, it was really fascinating because I would say they don't have room for error, okay? So they're not marketers, they're not, I don't know, you can go right and left. This is kind of human life, and I think it's important to understand why and understand how we get there. The disease treatment planning in particular was fascinating. So understanding that and seeing how, thinking about patients and how the effective treatments are done. So think about it. This is actually the real world example. This is what happens. It's not just 2 boxes or 3 boxes, and this is how the treatment and the outcome happens. Actually, you start with a treatment regimen defined. So this happens at the beginning of the treatment. Then you go, you have a treatment of some sort, then you have tests and scans, understand things, then you probably see the tumor size here, and then maybe another treatment now, right? And then you have another test, and all this keeps going on, right? And you keep looking at the tumor size. And probably I'm exaggerating a bit here because we don't have so many points, but the reality is that the models are the same. It's time dependent. The treatment that you have here depends on the treatment, depends on the tumor size, depends on the test results. It's not just in vacuum. If you make only one decision about one treatment and you think that you got it, you did not. Same thing for us, by the way. If we think that we put our emphasis on having a treatment, that means interacting with the customers and try to basically increase revenue in one shot, you may be able to get it once, but you will lose your customer, because you're just optimized for one treatment. So now think about it. I just changed a few words here. I changed the regimen by an assignment, a treatment by an adoption, test results by other metrics, the tumor size by revenue, the doctors by sellers, and the drugs by offerings. And I get the same picture. The same picture says is basically you assign our customers to a central program, then there will be an adoption of the offerings. We will have some variables here, co-funding variables of some sort. We will watch how revenue goes, and then there will be another adoption, and things keep going, and you will see how complicated those influence arrows are. Well, and eventually, if you want to change the regimen, this is the equivalent of changing the assignment to the program. Now, things are also not as simple. If you recall, I probably did not cover that one. You see that when we talk about treatment, it's not one thing. It's not a 1 or a 0. The treatment is multiple doctors recommending different treatments of different dosages. It's complicated. But it's also complicated in our world because when you have an interaction with your customers, you're not seeing it as a 1 or a 0. It's actually also, there are different sellers. Sometimes they show up, or reps, they talk to clients together, right? Remember I told you there's a specialist there? Also, they have different offerings that they are talking about, as well as sometimes these reps, they may follow best practices just like they may not. Think about the dosages kind of idea, right? They may not do the right thing. So what I want to say here is that there are emerging research opportunities in combining traditional causal inference techniques with AI models. There's a huge thing here. Big opportunity. We do feature balancing, structural linear equations, propensity matching, Bayesian models. We have been doing something of the sort. But then there is also machine learning, deep learning, encoder, decoders, transformers. All these are actually coming out, and I'm seeing research actually using the latest and greatest and trying to solve bigger problems at scale. Now, so what do we do about it? So I'm going a little bit into the mechanics of what we do. That means how we are building a product that measures the impact or the incremental metric that we're talking about here. And that's very different than having basically an ad hoc kind of analysis, right? It's not experimentation. So it's kind of, you have to go through the diagnostic, identification, modeling estimation, validation or refutement, and refinement. Now, let's talk about the first one. And some of the speakers before me have spoken about this. How to basically do the discovery. Diagnostic, you call it anything here. I think what's important is that there are different ways to do it. You can do it simply by expert opinion. You can do it by causal structural learning. And you can do it by LLM-based discovery too. Or you can do all these. Now, you can start easily. I don't think LLM is working for us because it's kind of very specific case. At least it's very narrow. But there is room for using the causal structural learning as well. And using graph databases there. Now, the modeling is using the DAG, the direct acyclic graphs, to understand exactly what are the relationships and trying to kind of link all these together. The pitches, the actions, the variables, the outcomes, and eventually how all this influence each other. And then comes the model. What model you'll be using? Because it's causal, we have to always think about the propensity network. So with the propensity network, it's important to think about the inverse probability of treatment as well as the prediction network. And you probably have seen it in different places, but this we can take it to a whole different level. Now, this is a question that I heard many folks asking the same question, which is, how do you validate your counterfactuals? And there are many techniques of refutation that are used. It's kind of common literature, nothing really secret here. It's actually looking at different tests. From sufficiency test, SOTFA test, placebo, dummy, variable. So basically, it's a sensitivity analysis to make sure that when we play with these things, we get the outcome that we expect. And that's one way to actually do the validation of counterfactuals. Now, easily said than done, because it's a whole simulation that has to be done whenever the system is very complex. Now, I'm getting into the last slides here. This wouldn't happen also within a data science team. We still need support. We still need adoption. So it's important to have support from the business so that you get at least the guidance of what the problem is and what the assumptions are, but also get in a science advisory board. Basically, the greatest folks who are around who can understand causal inference and kind of show you your blind spots. Finally, the journey continues. There are a lot of challenges. I wouldn't say it's kind of done. Nobody have figured it out yet. It's kind of research. The time variant treatments is probably question mark. Heterogeneity of treatments. Explainability is a big thing. As I mentioned, my business partners are always looking for why and how can I make it better. We talk about hybrid approaches. We always talked about experimentation aside and the counterfactuals aside. What about if we have both? Some programs will have basically holdouts and others they don't. And finally, we did not talk about quality of data here, right? Data is super important. To get it right, you have to have the right data, you have to have fresh data, good coverage, and that's necessary for your success. And to basically kind of wrap up my talk, if there is anything I would like you to take away is that we really there's a lot of excitement around science. At least on my side, I'm kind of being pushed to do even more and more for my business partners, which is a great thing to have. But also, there is a huge potential to make effective decisions at scale. And just don't forget that cross-pollination, cross-disciplines is critical to actually advance the field. So with that, I will end my talk, and thank you.
Thank you. We're going to squeeze one question, if that's okay. It's a big question, though, but I'd ask, yeah, can you do it in 30 seconds, right? How do you avoid local optima with many, many A/B tests that have small effects and are adopted incrementally, leading to bad global outcomes? So it's that.
That's a loaded one. So we don't have a so the I don't think I talked about this problem of having many A/B tests. So I think we try to make sure that the A/B tests are not corrupted by other A/B tests. We want to make sure that there is the integrity of the holdouts. We want to make sure that we kind of have some hierarchy in how we are deciding about the different tests. But that's at least to answer the question of having many A/B tests at the same time. The rest of what I was talking about is much more on the counterfactual side. So these different refutement tests are actually much more about counterfactual because we don't have basically a truth. We don't have any kind of holdouts that actually anchors us. So that would be the answer.
Perfect. Thank you. Appreciate it.
Thank you very much, Maher. And next up, let's welcome Adam Plumpton, VP of Global Planning at Cisco, for a fireside chat on how Cisco is using Causal AI to identify the drivers of customer demand and take a proactive approach to demand planning. And this will be hosted by Jerry Stevens, causaLens' General Manager and Retail and Consumer Goods Leads. So please remember to submit your questions via Slido, and welcome Jerry and Adam.
Thank you. Thank you. I don't have any jokes. I'm not really good at that, so I'm not even going to try. Do you have a joke?
I do not.
Okay, very good. We'll just cut to the chase then. I guess the joke is on us. We're right before lunch. So that is the joke that we have. So the first thing is a matter of introduction. So as Danielle said, I'm the general manager for a few different verticals. My background is in CPG and retail primarily, Procter and others. But I ran software for IBM. In North America for a while. So I've been part of a big community. And then I jumped into the startup world, I don't know, about 8 years ago. And probably in that picture, I had dark hair. And you can see what the startup community has done to me now. So that's a little bit about me.
Yeah, I'm Adam. I lead the planning function within supply chain operations at Cisco. I'm about 25 years into my supply chain career. I have done that at tech companies like Cisco and HP, at tech/automotive companies, Tesla, and at an additive manufacturing company called Carbon 3D. So I've seen the supply chain problem from a couple of different angles and have had a bunch of different roles over that period of time.
Yeah. So I'm excited to ask Adam a couple of questions because he does go very deep, and frankly, Cisco goes very deep in the supply chain space. In fact, I think Gartner's identified Cisco as a leader in supply chain for the last number of years. So that's something to be very proud of. And I know Adam's a thought leader in the space too. So I assume a lot of questions will come kind of after the Q&A here. And then the other thing is demand planning in general. When I joined causaLens 2 years ago, I always thought that demand planning in general was a very, very good use case. And it is because it sits in the middle of supply, obviously, and the creation of demand. And the way that I think about it is the pipeline, right? If you can get that right, then you build the pipeline from there. And Adam will speak a little bit to that as well as he kind of builds the future for Cisco. So thanks for taking the time.
Absolutely.
I really appreciate it. And we try to think of a theme. So I think the theme that we thought about when we connected last week was it's a journey, right? So Adam can speak to his experience and the fact that it has been a journey. And he'll take you through that a little bit as we kind of go through the Q&A as well. Okay. So with that as a setup, Adam, a lot of people in the last 2 or 3 years, a little bit before, but certainly last 2 or 3 years, have talked about the idea of a resilient supply chain. Yeah. Can you speak to how Cisco is approaching the idea and the building capability around the resilient supply chain and how Causal AI comes into that play?
Yeah, absolutely. And resiliency can mean a lot of different things in different contexts, right? And for us in supply chain, it typically means, are we able to produce and deliver the products that customers are ordering? And that resiliency is against some sort of disruption, whether that's a supply disruption, a demand disruption, whether that's driven by supplier solvency or a geopolitical issue or a labor issue, or you name it. And in trying to think about how you you build insurance policies or practice to give yourself more resiliency, fundamentally, usually you're making trade-offs about investment versus risk, and some sort of perspective on demand is relevant. It always is. And so at the simplest level, it's about providing to each of those scenarios or questions a view on demand at the right granularity over the right time frame, and that's where my team is often pulled into the conversation. And we will talk more about how we're leveraging Causal to do that, because candidly, the organization, my counterparts who have your old job, Jerry, that time perspective is usually pretty short, and the resiliency horizon that we're talking about is usually quite long. And so, we're making decisions as a supply chain organization and building models and forecasts that are far, far longer than the business's current perspective. So that's relevant. And I think that the second piece that maybe is less obvious, or maybe it is obvious to this audience, is in our causal models and our forecast models, if we can more explicitly articulate our best perspective of future error ranges, we'll do far better than looking at what ranges were in a rearview mirror. So those are two areas that are important.
Yeah, and your supply chain is very complex.
It is.
Yeah. Can you speak a little bit about that?
So to give you a sense, and I think it's relevant. It's everyone's supply chain is complex, but ours, we sell about, if you go on Cisco.com, or if you're a partner, we sell about 40,000 unique items. That translates to about 10,000 different things. So we're the physical portion of the supply chain. We sell in 200 odd countries. We do it largely through both an internal and a partner-led sales force that are portfolio sellers. And so there's not a whole lot of direct feedback from the sales community on item 1 or item 5,000 or item 10,000, right? You're not getting that level of granularity. And I'd say in addition to that, the levers to influence demand and kind of shape demand are pretty low. Most of the buying decisions are not based on whether it's in shelf or whether it's 5% cheaper. It's about something more complicated and longer time horizon than that. So it's in some ways kind of more of an open loop forecasting system that we've got to satisfy 10,000 products with.
Yeah, I think it's an important point as we start to dig into causal AI, because a lot of the people in the audience who may just be getting started with the idea of causality, and because I really believe that similar to what Judea Pearl was talking about, which is how we build out this kind of universe of causal applications is applications. It's things in production. It's models being used. It's value being delivered. And I think that is when we start to pull the train, if you will, the individuals who want to be part of this ecosystem. And in regard to that, let's talk a little bit about causality with regard to what the Cisco team is doing in causality, specifically to the supply chain.
Yeah, absolutely. And there's 3 or 4 of my colleagues who actually do the work. I'm talking about the work. They do the work sitting in the audience. Fundamentally, there's a bunch of different things we've done. I'll kind of group them into 2 categories. One is building aggregate models by business group at a 1-year offset that are enabled by feeding our causal models with thousands of different features or sets of time series data. And in doing that, generating a causal forecast, again, at 1 year out relative to the data set that you're inputting for what that business looks like. Now, that doesn't directly enable the team to go buy the right mix of parts, but it surely helps us understand and get a different perspective on how volume could be shifting. And that's immensely valuable. Second thing we're doing is with the same sorts of time series, but with different models, and in some ways with connected models that are correlating, building mixed level forecasts at that unit level, really with 2 goals. One is for the long tail of those 10,000 parts, I would love to have the output of the causal model be the forecast and have it be a no-touch process. And that's not for the sake of eliminating the people in the process. It's for the sake of enabling the planners in the process to focus on the higher impact left side of that Pareto. Yeah. The second part is to give a causal stream into that left side of the Pareto so that in addition to all of the other inputs that those planners have, they've got a robust causal-based forecast stream that they can use to ensemble or in a consensus type process to ideally improve the output of that forecasting process.
Yeah, and you can run counterfactuals and learn and build better strategies moving forward.
Absolutely.
So yeah, I love that application. It's very exciting. Can you speak to maybe some of the challenges? So this is not an easy button.
Yeah.
We all know this. This is not, hey, we're all of a sudden, causally driven and all of a sudden everything is explainable and transparent and we're ready to go. It is a journey. Yeah. Can you speak to maybe some of the challenges that you had to, or that the team maybe has overcome, or maybe is still overcoming to this day?
Yeah, there are a few. Most have come up throughout the course of the morning already, right? We're talking about a lot of data. So, staging, organizing, transforming, just kind of the operations of enabling this are not insignificant. It takes time. And it takes, some care and feeding and leaving alone to experiment and develop models and build confidence and test and expand. So that component is not trivial. And I think once then you start to catch the tiger by the tail a little bit and get people's interest, there's this pull and thirst. It doesn't change the fact that it still takes time. So prioritization and striking a balance between productizing and delivering something to the organization, which in our case is a repeatable exercise that has to happen every week or every month, in addition to continue to experiment and expand your scope, is a balance that we've got to manage well.
Yeah. And can you speak to maybe some of the benefits as well that you've seen as you've gone through the journey?
Yeah, the first is the obvious one on performance. And we did this, the team did this in an interesting moment in time. We were doing this during the course of COVID when our demand patterns were just completely out of whack from normal historical patterns. And they built models trained with pre-COVID data, and they were remarkably accurate in comparison to all of our other forecasting approaches. And so that was shocking, and that got people's attention. Yeah. The second thing that is then, and everyone has said this, and it's obvious, it's the why, right? And sometimes those whys they make sense, and you say, oh yeah, okay, that makes sense, and you can dive deeper. And sometimes they don't quite make sense, and that I think helps inform a dialogue that maybe improves the second version of the models, and maybe causes the business to think about other things. Yeah. That process has been pretty rich.
Yeah, and we see that a lot as well with other clients as well. It is a journey depending on the use case. Yours is obviously very complex in terms of demand forecasting across the global enterprise, thousands of SKUs, multiple timeframes, multiple periods, multiple decision makers. You have suppliers, you have customers, you have vendors. It's very, very complex. So it is a journey. We see that all the time, but I do think it enables people, number one, to understand their data better, for sure. Where are we missing data, maybe? And then the other thing is really asking questions that you're not asking already, I think comes to play as well. Did you experience that?
We did, and I'd say we did it both ways. Maybe one example is, not surprisingly, some macro factors were key causal drivers that we pulled out of these models, and that's not surprising. In the back and forth, it's like, well, you know what? The dynamics in this particular region are very different than that particular region, and that dialogue is kind of reframing the next couple of quarters probably. And rather than building global models, or in addition to building global models, we're going to build some geographic centered models. So that's an example. Maybe another is we have a business perspective that kind of the hangover of the bullwhip that was COVID, right? So from a tech perspective, demand spiked, lead times were extended, companies accumulated backlog. Supply eventually got healthy. We shipped that supply to customers. That doesn't mean that a customer who just got 10,000 access points is able to go install them. Now there's this consumption issue where that, the mouse has to work its way through the snake.
Sure.
We didn't anticipate or model that in our causal models, but the dialogue prompted us to try to pick those types of effect up as features and build them into the model. So I think I can see examples kind of both directions.
Yeah. So what's next? You guys are, I think, at a pretty good point, production, et cetera. So what's next in terms of the causal work?
We've got plenty of room left to keep building out this as part of our forecasting practice. There's a lot there. I kind of joke that each quarter when we do a roadmap review, the font on the page gets smaller and smaller.
That's true. That's true.
It really is true. There's also a lot of adjacencies that are super relevant even within supply chain. We're focused on the demand problem. You could think about the inventory problem. You could think about, there's plenty of logistics, examples, pricing, for supplier commercial relationships. There's an endless set of possibilities.
Yeah.
So that the challenge is prioritization.
Well, that's why I like demand planning. There's upstream, and we think about it in terms of developing a pipeline, right? So once you're able to, and it's somewhat modular, right? Think about it as a modular kind of environment where, hey, we've kind of demand planning, we have causal models that we're very happy with. There's pipelines that we can build on top of that that go to upstream and downstream impacts and effects and decision making.
Right.
And that's the last question I have for you, is because ultimately the idea, the goal of what we're working on is to enable better decisions, right? And that's what we try to do. That's what you try to do. That requires trust, right? A great deal of trust. So how have you navigated that within the Cisco organization?
Yeah, I think the biggest piece of that is time, candidly, right? To give yourself the time to, let me step back for a second. I think there's layers of that, right? There's the demand planner, so an individual contributor who's got their own perspectives, they've got a marketing input, they've got what happened yesterday, and they've got, 2 or 3 different machine learning streams, one of which is our causal stream. How do you get that person to understand what this is well enough so that they're picking it out and they're making a critical evaluation? So there's exposure, there's learning. On the demand planner side, for the data science team, I think for us, it's been really, really important that that team understands the planning problem. So they're talking to their customers in a way that enables that learning and connection to happen more quickly.
Yeah.
With both that community and then as you roll it up the ladder, we do a quarterly readout to the CFO, and I include a slide or two on our causal perspective. And explainability, transparency, causal factors, the relevance of those causal factors, those are all important things.
Yeah.
And at the end of the day, model performance kind of matters too.
Yeah. Well, yeah, it starts there, doesn't it? Yeah. Certain level of accuracy is required to make decisions. Well, that's all I had. I do want to thank you and appreciate you spending your time with us today.
Absolutely.
And definitely want to open up for any questions.
Perfect timing. So a couple of minutes just before lunch. First question, how do you implement consistency across multiple structural causal models that may exist for the hundreds of different products that you have?
I think that's both one of the challenges and maybe one of the okay. I think we're thinking about it a couple of different ways. Let me take 2 different examples. One is we do run aggregate models by business at a dollar level. And those are, like I said, helpful in thinking about the size of the business and comparing against our unit plan that's generated other ways, bottoms up. It's helpful to think about volume trends, which is super hard. Additionally, we're building unit plans, right? So just driving correlation between those two is one approach. I mentioned the regional thing earlier. We're running things like there's a Puneet who leads the team, has a cube, and we're running it kind of by business, by region, and there's a third dimension. I guess it's by layer in the stack, level of granularity. Those are going to end up with different answers. And candidly, we see richness in that. And so at some level, I think we're leaning into the fact that these different models aren't necessarily all going to be correlated, and the why is going to help us, dial each of them in to a better extent.
There are a few more questions, but I'm also conscious what time it is. So what I was going to suggest is those who have the questions, unfortunately, you submitted them anonymously. Please grab Adam or Jerry over lunch. But otherwise, I think we should say thank you.
Thank you.
Thanks, everybody.
Save the live stream.
Huh?
You want to save the live stream? We're going to take a break.
Oh, okay.
Totally.
Straight back into our agenda. So please get ready for our panel discussion with Abhi Mukherjee, Senior Economist at Amazon, Ching Wu, Director of Econometrics at Google, Tilman Drurup, Director of Machine Learning Engineering, and Wei-Jing Jan, Tech Lead at Ecosystem Data Science, as they share their triumphs and challenges in navigating the causal AI space, and moderated by causaLens' Associate Director and Head of Partnerships, Alfonso.
Awesome. Thank you, Danielle. Should we start by doing a quick round of introductions? So do you want to introduce now?
Sure. Hi, everyone. My name is Wenjin. I'm a principal data scientist at Roblox, and I lead our ecosystem data science team. Currently, we own the analytics of our centralized experimentation platform, but our team is also in the process of really scaling that into a comprehensive insights platform on bringing different causal models, forecasting, root cause analysis, and analytics tools in a way that we can support a diverse set of users, not just technical data scientists, but also, the goal is also to have more of a self-service PM stakeholder-facing interface as well.
Awesome, thank you. Hey, I'm Tilman. I'm Director of Machine Learning Engineering at Instacart, economist by training, and I lead the economics team at Instacart that supports horizontally all parts of the company. I could talk a long time about the stuff that we work on, but I'll skip that, so please hit me up later if you're interested. Also, I'm hiring.
This is Ching. I'm in charge of the team called Econometrics. We report to our chief economist and also reports to our president directly. So given how large the company is, we are pretty lucky to sit on top of every PAs. We kind of pitch our consulting services and also tools and the methods to anyone who wants to use our methods. And yeah, we primarily focus on causal inferences. Yeah.
Hi, I'm Api. Nice to see everyone here. I work at Amazon on the economic valuation and optimization team, which, as the name suggests, works on valuation and optimization. Yeah, I can also go into a lot of depth around like what our team does and like how we work with Amazon, but let me stop there.
Awesome. Thank you, everyone. So I guess we can start with an open question, which is what motivated each of you to focus on causality and causal inference methods?
My background is actually in biostatistics and public health. I did my training across the Bay at UC Berkeley on biostatistics, and most of my research in my PhD program and postdoc was on public health and precision medicine, and also in HIV prevention. So a lot of things that Maher talked about on chronic care treatment resonated very much with me. So from there, in those applications, really not everything can be A/B tested, and a lot of times, even if you want to A/B test something, to generate some hypotheses and candidates to test, you do need the observational causal inference to do that. And even within A/B tests, right? It's not like once you can test, then everything is golden. There are still questions of how do you extrapolate into longer term effects? How do you understand treatment effect heterogeneity? Or causal pathway through mediation analysis. So there are a lot of questions here that you just need to have where causal inference comes in.
Sure, I can try. So I'm an economist by training. So as an economist, I'm naturally interested not only in understanding how the things are the way they are, but also in understanding how things could be if we change the state of the world a little bit. So I've been working a lot on questions like pricing, incentives, and so on. And all of those are intricately linked to causality in some way or another. So, that led me to it, and it's been an exciting field. So, yeah.
Ultimately, I think we're trying to help the decision makers to make the right decisions, and these decisions have a lot to do with like the causal impacts and also the program evaluation and policy qualities and all that stuff. I think that's sort of ultimately inspire us to do more like both like experiment and observation studies to provide the leaders to make the right decisions. Yeah.
I also come from an economics background, so it kind of the empirical aspect of the field really revolves around causal inference. So I started with kind of more reduced form traditional approaches, and from there, machine learning and applications of machine learning and deep learning to those problem spaces. Yeah, so I think similar to Tillman in terms of background.
Awesome. So, Wenjing, not many data science teams have experimented with causal inference before. How do you recommend they go about kind of building this practice internally and getting internal buy-in from senior stakeholders?
Yeah, I think it really depends on where the data science journey is in each company. But I mean, obviously, a lot of companies start with having an analytics function, just surfacing very basic business intelligence, and then they graduate into having an experimentation platform. And then inevitably, there are business questions where you cannot be answered by by experimentation. So that's where observational causal inference come in. But I think across all these different steps of that journey, no matter what stage you are, the strategy is really just that two-pronged: show value and very cleverly demonstrate and communicate value. When I say show value, it's working, having, I mean, data scientists need to have, right? We're not just here to code up a problem, right? We have to have very deep context with the business, really be able to understand what are the key questions that the business needs to answer, and then find opportunities where we can show some, where we can answer those. Let me just give a very concrete example, right? So we want to know what are the drivers of churn in a Roblox system. You can run some pilot project to using observational causal inference to identify some potential drivers, and then from those rank those drivers, and then develop some tests that you can validate these hypotheses. So when we say, right, how do you, the value is answering the questions through actionable insight. What is actionable insights? Like, be more concrete is something that you can test with a product. Like something that I can come up with a product level, a product feature that we can test on. So this is one way we can showcase value through pilot projects and then have many iterations of those, but also be very be a bit in terms of how you communicate these insights, and you need to be able to talk at audience at different levels. Your data scientists need to be trained to not just go deep in the technical details, but also be able to zoom out and talk to your non-technical stakeholders in a way that is more business focused, where they can understand the intuition behind the methods, but more importantly, the implications of these insights. Yeah, so I think, so that's them showcasing and communicating some of the values. And then the other part, it's also that continuous culture shift to know that we're not advocating, this is not like, experimentation is not the smoking gun. Causal observation is not the smoking gun either. It's not one versus the other method. It's really about the company continuously building out a diverse set of toolkits, right, to have a body of evidence. You sometimes don't really have a concrete 95% confidence interval static treatment effect, right? But it's really, okay, maybe with 80% confidence interval, we have a directional read. That is good enough for us to inform the product to move in one direction versus the other. So it's communicating that tool set diversity that companies should have. One second.
Like Google has been running online experiments for a very, very long time. So on the product engineering side, the experiments has been their like golden standard. But on the business side, right, I'm talking about sales, marketing. Early on, my colleague actually presented like, you know, what they were doing in the GCS sales side. So the business side at this moment, you know, they're not fully aware of the causal inferences of how the power of it, because most leaders, you know, grew up in the sort of older days, and they're just not aware of how they make decisions. Underneath that decisions, actually a lot of causal inferences behind the scene. So we are trying really hard to sell our technology and our methods to them. Also, part of our job is to educate them, to make them aware that you can take advantage of other types of experiments, all observational data, or natural shocks, and quasi experiments to really get better insights before you make the final decisions. So that's definitely, I think it's not it hasn't been that easy, as I said. Like I think this is ongoing work, and I think that there's a trend of tech firms hiring economists, right? People ask why they're hiring them. I think that's because economists have been borrowing their tools from the public policy side and program evaluation side, and push them over to the corporate setting and make the business leaders to make the right decisions. So I think that's an ongoing trend. We're kind of riding that trend, and hopefully, more teams, more PAs will embrace these methods and the processes. Yeah.
Yeah, I think one thing I'd add to that is part of the challenge is that there is fundamentally no source of ground truth in a lot of these problems, particularly when you're looking at observational causal models. And so like I think Amazon and most tech companies have been doing A/B testing for a very long time. That space is pretty intuitive. But when you think of like more obscure problems that can be framed in causal terms, it comes down a lot to sort of advocating and communicating and explaining how exactly something would in fact be a good way to think about making decisions. Like what I've experienced is that like once you kind of do a few of these, like the initial ones are pretty hard. Like you're kind of really struggling to look for like a problem space where these things are applicable and valuable. But once you've done that, like at least in the big companies, I think what ends up happening is that more and more people get interested, more and more people see this as like something that would help them sort of optimize for their own business processes. And I think that's kind of how it goes. Yeah.
You guys got some of the most famous people.
We try, yes.
Yeah. And I think that ties in quite well to my question to you, Tillman, which is what are some of those challenges that you have seen when adopting this journey?
So at the risk of being a bit confrontational, I think the modeling part is typically fairly easy. Like setting up a model, running an experiment. It's not trivial, obviously. There's a lot of hard work and good work going into this. But I've seen a lot of models or causal approaches fail silently once the model is tested and rolled out. Because typically models turn into orphans, in particular causal models, once you roll them out. There's nobody watching them. Nobody makes sure that whatever your causal estimate is once it's rolled out in production, stays true in some way. So building this muscle that you build a causal model and optimization framework on top, roll it out, and then keep check of what's happening once it's in production, that there are no emergent phenomena, that there's nothing else happening. I mean, your product is evolving all the time. So your causal estimates are evolving all the time. I've seen this on multiple occasions, in particular when the roles between data scientists and MLEs are not entirely clear, that models, they don't get abandoned. They live their life out there in the world, but nobody's really looking at them. And I've seen a lot of projects fail in this way. So I don't know whether others have seen similar effects, but that's something that repeatedly shows up. You run an experiment, the experiment looks great, you roll it out, and there's no plan for after.
Yeah, I think even we have experiment rollouts and then we run internal holdouts after that. But we have like 6 months, year holdout depending on the team. And oftentimes what you see in the holdouts do not necessarily capture the things that you see in the experiments. And that's always a challenge, right? It's one around whether our test conditions actually reflect what happens in the wild. And then the other one, I think, also comes back to some of the things that we talked about earlier is, so your experiments, even analysis, happen in a short period of time, 1 week, a few weeks of an experiment, but the underlying question that we're interested in actually long term. So how do we do that extrapolation, right? That's also one of those causal questions that we don't really have a good ground truth on.
Just to add to that, so we have found that probabilistic decision making helps us a lot in keeping this in check. So not only running a holdout, but making sure that we perpetually generate new training data so we can re-roll and evaluate different kinds of models as sort of the product evolves. So we can, using this kind of framework, we can always keep track of how a model is performing right now. And we can use the same data to train new models based on updated data and evaluate, off policy evaluate different kinds of models and how they would work. It raises the bar on the technical side quite a bit, and it requires you to convince stakeholders that even after an experiment has been run, you kind of want to waste a little bit of money all the time to generate more and better data. This has been something that took some convincing that this is worthwhile, but we found that it's definitely worth it, and blog post coming out on that topic soon.
Yeah, we just had a long sort of internal discussion based on Angus Deaton actually came to Google and gave us a talk. He has a very famous paper about like he has a lot of reservations about RCT, and internally we also have seen a lot of these RCT results. Sometimes don't seem to make sense over the time. So there's a lot of limitations about RCT, A/B test. There's various different strategies to sort of mitigate its potential harm, or just take advantage. It's whatever is the best. So I think it's still ongoing debates. All these different strategies or methods out there to make sure RCT is still run, but make sure the results are used properly. Yeah.
Yeah, I think one other challenge is even if you have like the holdout samples and all that stuff, one of the challenges comes down to backward compatibility of methods. So as the field is evolving, like methods are improving, methods are evolving, and none of them are perfect. You're making assumptions, you're introducing some subtle biases that are not always easily apparent. And then when you have a business stakeholder who's already been using your causal estimates, particularly for like large decisions, and now you've rolled out a model, but things have started to change, and it's not always easy for you to say, it's changing because of X or Y or Z. I think that also makes it difficult to build confidence sometimes.
And Abby, what are some of the kind of areas where you've been applying causal inference to, and some of the most successful use cases you have seen?
Sure. So I work primarily with observational models, as I said. We kind of view it as like structural causal modeling, really. So it's sort of like we specify a dynamic graph structure, and then we think about counterfactuals, which can be constructed by removing sort of nodes or sets of relationships there. And so we apply that pretty flexibly to a lot of different areas. I think some of the ones that have probably been major areas of focus that we've sort of seen a lot of interest in have to do with valuing product lines, valuing product launches, marketing applications in terms of, like are investments worth it for the company. So I think that's kind of the space that we've been in, and now we're kind of looking into going more granular there and helping with optimization problems around like what should you even be doing going forward, like when it's not even a clearly framed question.
What about the rest of you? Similar areas or?
I think we've been fairly successful in applying causal inference, in particular heterogeneous treatment effect estimation for areas like incentives and personalized targeting and so on. It's fairly standard. We're also fairly excited about the potential in paid marketing, where we're operating with bandits. Have some cool stuff happening there, and it's proven extremely impactful. Yeah, anything?
Yeah. I think we have a few success stories around what I alluded to earlier. The hypothesis generation is identifying potential. So we are in the process of building out really a metric hierarchy or some very coarse understanding of what the business stack will look like, right? So here is a company North Star. The next layer of direct drivers, and then the next layer of drivers of those. So in order to validate those, we try to identify some kind of encouragement A/B test that can help us move some of those drivers. And in some, we are seeing some success stories of some of these drivers and relationships being confirmed with this encouragement A/B test, but there are some others that is just we haven't been able to, right, because the confidence interval was too wide in the original analysis. Similarly in the IV analysis, that we can really have any definitive answers.
We are trying to move beyond just the binary treatment at this moment, because we're moving towards the continuous repeated treatments. Also, like I think Maher described, like in his organization, his clients or his advertisers are just like a patient, needs continuous dosage of treatment. It's also it's a vector. It's not even just one number. So these are much harder problems. And also imagine if you want to get some confidence, it really needs a lot of data. But also we think these type of problem definitely is very important for operation of the company, like such as how do you allocate resources properly across different PAs? How do you optimize your operations for your clients or your users? I personally feel that space right now is still not as explored as the binary treatment world. So it is definitely very challenging given the small size of data and also the noise out there. Yeah.
And well, a few of you are economists, but Cheng, how have you seen the emergence of machine learning kind of impact traditional econometrics techniques? And
Yes, definitely. But I think in a lot of our business problems, definitely we're suffering two things, right? Number one, the measurements are not accurate. It's not accurate. Lots of missing variables. I think because of those problems, like machine learning can help, but it's very limited, right? Because we just don't have enough signals. So we actually find out a lot of these traditional difference synthetic control or RD methods actually work reasonably well because they don't require a lot of covariates. So that's what it is. But in the space, we have a lot more signals. We definitely will try to use ML quite a bit, using either double ML or BART model or sort of double robustness, like propensity scores. Definitely, we use them if we have enough covariates. But in the situation that's really hard to collect them, we kind of have to resort back to the more sort of traditional econometrics models. Yeah.
I think in tech, at least, like there is a lot of, I guess, talent and expertise in machine learning that becomes useful, and at some point it becomes optimal for the company also to think about, like, would this machine learning engineer be optimally invested in improving a predictive algorithm by like 0.01%, or should we kind of think about trying to integrate it into a causal estimate that might be more valuable? I think the field of economics is generally a little bit slower to adopt new methodologies. One of the reasons why the traditional ones have been so successful is because they've been so well used and so well studied. But I am seeing that's kind of changing. Like there is definitely more interest even in academia in terms of introducing new machine learning based methods in kind of more traditional problem space. Yeah.
Awesome. I guess it's an AI conference and everyone's thinking about Gen AI nowadays. It's top of mind for many executives. Have you seen it impact your causal journey, and have you thought about kind of interfaces between generative models and your causal models, or ways of leveraging both together?
So I guess let's see. What can I talk about? I think what we found is there's a lot of world knowledge embedded in these large language models that can feed as input to other causal models. Like all the attempts I've personally done at using LLMs for causal inference type scenarios have failed, like from the LLM self-confounding or making nonsensical recommendations. So, plain vanilla LLMs haven't done it for me. However, what LLMs can produce in terms of structured knowledge about the world has proven fairly impactful. At Instacart, we work with tons and tons of catalog data. And if you ask it questions about certain parts of the catalog, how they relate to each other, you often get extremely good responses. Like as an economist, I'm obviously interested in things like, which of these things are complements and substitutes. And you ask it for huge matrices and you look at a few entries and you realize, oh, this is flawless. So that's what I found pretty impressive. That doesn't really solve the causal problem, but it can serve as an input for causal problems where you need a lot of covariates, for example, to describe differences between products and so on. Anything on?
Yeah, I think to add to that, for me, so far, where I see the most, our highest ROI is in that productivity boost and also in terms of feature engineering. But to actually deepen the causal structure, like being able to form a causal structure, causal understanding of an ecosystem, I feel that's really the Christmas wish list, but we're still quite far from that.
Yeah, I think it depends on the type of problem that's being asked. In our world, a lot of these impacts are like in the range of 1% to 2% and with pretty large variance. So yeah, I personally, we probably used LLM to brainstorm a little bit, but when it comes down to actual estimation and evaluation, I haven't found it that useful at all.
I'd say it's still early days also. It's difficult to, like the generative model structure, the transformers and things like that. Like, as far as a predictive tool goes, I don't know if that's where the real value is, and the generative construct really is not applicable directly to the causal space. I think what's actually interesting is the inverse of your question. Like, what happens when you think about causal structure added to an LLM to understand? Like, does it even make sense? Like, how should it think about what is a good thing to be saying in that context, and why is it even saying that? So I think that's probably more in the machine learning domain, not so much maybe in the causal space. But I think that's something that would be interesting, and there is work going on there. So.
Yeah, sort of like grounding the LLM on the causal model itself,
Exactly.
right? Awesome. And I guess on that note, what are some of the areas in the field of causal inference that you're most excited about? New research or?
So what I like is not so much it's not so much new developments as there have been things that have been used for very long, and now people are going into them and saying, okay, wait, are these assumptions sensible? Like, what does this estimate really mean? Is it an average effect? Is it an average effect on the treated, and so on? So, like we mentioned diff and diffs a little while ago, and so like one of those things that it's a few years old now, but like there was this paper which kind of shows that like essentially 30 years of research has been interpreting a causal estimate as slightly differently than what it really should be, and like how should you actually be running this, particularly when you have like repeated treatments. So I like I like the fact that like there's people who are sort of spending a lot of time reviewing things that have been taken almost for granted, and like how can we improve these. So that's something that I find pretty interesting.
Yeah, I want to echo that as well. I think causal inference has been around for a long time in a lot of fields outside of tech, right? Social sciences, health sciences, and even things that we use a lot in medicine, like time varying confounding. When I first got into tech, that like everyone was very focused on point treatment, continuous point treatment, or binary point treatment. So even like now we have software packages I know EconML has that, right? Just hearing all this, like the discussion is now moving beyond how can we best understand point treatment to how can we best model time varying confounding. So I think that's an example of the knowledge from different fields now start to propagate across the different tech companies, and that is really what helps us cross-pollinate and have more ideas generated and built on top of those. So that's pretty exciting.
Yeah, I think academically, I've seen a lot of new things out there right now, right? The missing variable problem, the Bayesian version of everything, and there's a sort of resurgence of the difference in difference. There's a lot of new take on difference in difference, and heterogeneity of impact. Like the causal tree and BART, everything out there, fast BART. Yeah, I think, and I mentioned earlier the continuous treatment, the dosage or the vector treatment. So I think, the academia is continuing to push this forward, and in the industry, some of the problems probably are inspired by the industry problems, because I know Guido spent a lot of time, and Susan Athey also spent a lot of time in Amazon and everybody else. So I'm sure a lot of their research were inspired by the real problems they confronted there. So our job is actually sort of bring all of them together, right? So that we can also use the data, use the methods to solve our real problems. Yeah.
Can I also be a contrarian here a little bit after saying all I just said? So we talk about things that we're excited about. One thing that I still see gap on is the gap between really cutting edge methodology research in academia and how that is implemented, or that gets how that is brought into the industry. Usually it takes a long time, right? All these things that we just talked about that we're currently excited in, they were developed years ago. So why did it take so long, and how can we accelerate that so that the next batch, the new batch of research can be implemented in shorter time frame going forward? It feels like, where is that gap and how can we close it? I don't know.
I think I do. So I think we found a fairly good way of getting fresh research ideas into the company. So every year when the economic job market happens, we go around and invite people who go onto the job market to present to our internal econ seminar. So they can be grilled by 15 to 20 machine learning engineers and economists. And we found this is a very, very rich exchange. We provide them with insights as to what the industry cares about, what the actual problems are, and we get from them a perspective on what's up to date in the industry as well. As to the topics that I'm very interested in, because you mentioned Susan's work, we work a lot on surrogates and contextual bandits. I think it's fairly advanced, and it's a lot of fun just kind of following what the literature is doing and taking it directly to practice. It's not trivial, but yeah, something I'm passionate about.
I think I was thinking about like why things move slowly. I think part of it is like in predictive models, there's like very clear measures, right? Like algorithm A is objectively better on like these dimensions. Like, I don't know, I think it's more challenging to frame. Like, how do you know that this latest paper from Professor X is actually better than whatever you've been using? Like, how do you even know that? Yeah, it's a challenge.
Awesome. So I think there are some questions from the audience.
So there's a few come through. Nice, easy one to start you with. So with AI, machine learning, and LLMs increasingly being in the general public discourse, do you find that it's easier or harder to talk about the value of causal AI to your business stakeholders?
I can take a stab at that. I think the challenge is now if you don't have the word, if you don't have the letters LLM somewhere in it, no one is interested. So I don't know. It's facetious, but I think it is a problem. Like I think the expectation of using the latest, almost I'd say, fad technology in every single application, no matter how poorly suited it might be, I think that becomes like almost like it's almost like a point of contention now between the person who's going to use it and the person who's developing it. Yeah, so I think that's a bit of a challenge.
Actually, I find it easier to sell right now. I brand Arima as AI forecast.
I noticed that.
Yeah, definitely. I did notice a change in branding from it used to be statistics and then causal inference and then causal ML and now it's causal AI. So let's see. I don't know what the next keyword is gonna be, but I guess at least in my case, there hasn't been a mixture or a conflation between Gen AI and causal inference, at least with my stakeholders. They're very, maybe because the way how we use Gen AI inside Roblox is very much around content generation. So the expectation hasn't changed on what causal AI can do. So, but still we have to continue. For us, it's more around the expectation between causal AI and experimentation and how to distinguish the quality of the evidence between the two. So that's continuing our problem, still our problem.
Right, thank you. So another one, nice easy one for you. Do you use causal discovery in any of your work? If so, why? And if not, why not?
Not regularly. There are specific cases where we do think about discovery, but in general, certain types of causal links are expected, at least in the problem spaces I've been looking at. They're you kind of know like what associations are not going to be useful and what are, and we can usually scale enough to try to allow for all of these, and then it's more of a question of like, do they actually bear out in terms of the association? But I think discovery is not something that I've worked with too much.
Yeah, it doesn't work that much in our business sort of context because actually the causal relationships, it's very complex. You know, sometimes it's really hard for us even to tell is A causing B or B caused A caused the C or some reverse relationship. So I think we do a lot of homework just to understand the business, understand all the associated sort of, you know, links to really get that causal picture right. So it's not, I don't think the LIM model will work. It's a lot of field study and sort of investigation with the stakeholders.
Yeah, we haven't gotten to it either yet. So I think our product is still changing quite rapidly, and a lot of the causal links that might exist today will probably not exist in the near future. Maybe at a future point in time we will.
Yeah, same here. Yeah, it's very much about having a very concrete hypothesis and really testing those local links.
All right. Picking out the questions that are more generally for the panel, there are a few that are being directed to individuals, but maybe we'll pick up on that in one of the breaks. But a question here, how do you see the connection between the econometric and data science teams within a causal inference perspective? I don't know whether the teams work together well or not, or what the question's for.
So Amazon has very conveniently completely split them. So there are economists and there are data scientists, and they do slightly different things. I haven't found it to be a problem working with people with different backgrounds. I feel like in the causal space, at least, there's enough work to go around in terms of like specializing maybe in the methods versus specializing in implementation side or specializing on the machine learning aspect of things. So I think, like, at least in my experience, it generally gels pretty well. I haven't seen any instances of that causing frictions or inefficiencies.
Yeah, and I think same here. So I've always been in the data science team, but then we don't really have separate economy. We have economy data science team, and there are economists there, but then we also have economists just throughout the whole data science team. I think it's data science such a broad umbrella, right? Economist is one type of data scientist, but in terms of, yeah, I never had any problem working with. I'm very surprised by that question, actually.
Yeah, Google actually has tradition hiring a lot of statisticians. The hiring econ people is relatively new. We do think like econometricians actually provide something very complementary. So each sides, have something, new to bring to the table. So I feel like the best strategy it is have both, and I think like econ people here tend to think a lot more about like incentives and unintended consequences and spillover effect. Stats people tend to be a little bit more focused on the p-value. Okay, hypothesis testing. Sorry, I'm not trying to pin it down. Anyway, just saying like I think both sides can collaborate. Be complementary by each other. Yeah.
I think we'll wrap it up at that one. That was a good one. So thank you all.
Thank you.
I'm just going to move the chairs while you.
Okay. Okay, thank you to everyone on the panel. I'm sure you've given everyone a lot to think about with that discussion. Okay, so up next, we've got Eray Turkel, senior data scientist at Google, who brings us a discussion on the pivotal role that counterfactual models play in effective decision-making.
Hi, everyone. Thanks for having me. My name is Eray. I'm a senior data scientist at the Google Econometrics team under Ching, who was just at the panel. And today I'm going to talk about how and why we should use counterfactual models in our business decision making. It's a pleasure to be here. It's a great pleasure to share the stage with everyone today, and thanks to the organizers. All right, this is a non-technical talk aimed at a seasoned practitioner, and I want to start with the big picture question of why do we need counterfactual reasoning and why do we need causal models in our business? So frequently in business, we need to make decisions between different kinds of interventions. We need to decide who should we target with our ads. We need to decide, should we run a marketing campaign or not? We need to decide who should our salespeople talk to, and who should they prioritize, and who should they deprioritize? And when thinking about these kinds of questions, I want to frame our model of the world and our thinking using these two questions. The first one is, what do we need to learn? And the second one is, can we actually learn it from the data at hand? So diving deep into the first one, what do we need to learn? Is this a predictive task, and can we make do with learning from historical associations? Or do we need to make statements about unobserved counterfactuals and decide between interventions? And once we've decided that we want to learn something, and hopefully that is a counterfactual, because that's usually what's the relevant thing in business decision making, the second step is deciding whether we can actually learn it from our data. Do we have any useful information or variation in our data set that would help us learn that? And what do we need to believe about our data and our data generating process for our answer to be actually the causal answer that we seek? And the main takeaway that I want to leave you today with is that causality is not a property of the model or the algorithm we use, but it is a result of our assumptions on the data generating process and our beliefs on the world. All right, so I'm going to jump into an example. I'm going to run through two examples, and because the organizers asked me to talk a bit about marketing and sales, the first one is a marketing example. So let's take a hypothetical situation where we need to evaluate the impact of our marketing campaign. Now, for simplicity, let's suppose we have no control over how the campaign was run. We are just tasked with this problem of evaluating its impact and deciding whether it was worth it or not, and figuring out a way to quantify its returns. Now, what do we need to learn to answer this question well? What does it mean to measure the impact of a marketing campaign? Well, I don't have to try to convince you really hard that this is a counterfactual question, and we need to know the counterfactual of what would have happened without a marketing campaign. And this is a question about an unobserved world. We live in the world with the marketing campaign, but we want to make inferences about the world without it. And it is very tempting to jump into machine learning in a situation like this. We collect a lot of data about our business. We probably know who interacted with our ads, who converted as a result of seeing our ads. We know how much our customers are spending. We have high resolution data, and we can train a machine learning model to predict revenue under marketing and revenue without marketing using different sources of variation. We can either teach it from the cross-sectional variation of the data, training it between cities with marketing versus cities without marketing, or we can leverage the time series variation. We can teach it using periods with marketing versus periods without marketing. Now, suppose we dived into a situation like this. We have a marketing campaign run on a city, and we see that the cities with the marketing campaign have X% higher revenue. As a result of our machine learning model, we produced the outputs under marketing and produced the outputs and predictions without marketing, and there is a difference. And the predictive ML model can help us make statements like the cities that had marketing campaigns had X% higher revenue. And this might be a correct statement, but it's not really informative for the decisions we're trying to make. And it's not really teaching us about the counterfactual. Now, there are many reasons why this scenario can go wrong, but if you bear with me a second, like a model trained on the cross-section can be picking up a bunch of other factors, and I'm sure you can come up with many other explanations here, but one of the potential reasons how this can go wrong is how do we choose where to run the campaign, and are we picking up the effects of us choosing a city with an established organic growing user base versus the actual effects of our marketing driving growth? Can we distinguish these two things from the data at hand? Now, this is where counterfactual modeling comes into play, and this is where causal models are useful. Well, we need to learn what would have happened without the campaign. How do we do that? We can construct a causal model or a counterfactual model. And there are many, many things in our toolkit to do this. We just talked about synthetic controls, difference in differences, modern approaches to difference in differences with Callaway Santana, other panel models. We can construct a counterfactual prediction using any one of these things in our toolkit, and hopefully that is going to get us a causal answer. Or if you're lucky enough to run a randomized control trial, you can also pick a random subset of cities to run your marketing campaign and randomly pick another subset for the holdout and try to learn the counterfactual from those who didn't get the campaign. Jumping into another example here, this is about sales and touches a little bit of what my colleague Maher talked about this morning. So suppose we want to understand the impact of a sales pitch. What is the impact of our salespeople pitching our product to our customers? Again, this is a counterfactual question. To answer this well, we need to understand what would have happened if we didn't do any sales interventions. And it is a very rich, data-rich domain, and we potentially observe how our salespeople interact with our clients, how many phone calls they made, how many of those got answered, how much our customers are spending, what was their spending trajectory. And again, we can use our rich data set to build a sophisticated ML model. We can throw a neural net at this if we want and try to predict what would have happened with the sales intervention and compare that to the prediction without the sales intervention. But again, going back to the question at the beginning, what is such a predictive model learning from? It is learning historical associations between sales and revenue and learning from the differences between clients that receive sales pitches and clients that didn't receive sales pitches. So do we have any useful information or data to help us answer the actual causal question of what would have happened without the sales intervention? Can we use anything, any source of variation in the data to help us distinguish between organically growing customers being pitched to versus salespeople actually driving growth themselves? Now, to answer these things and try to get around them, we can again go to causal inference modeling and model counterfactuals using some kind of propensity model to account for selection into receiving a pitch based on observable characteristics of the advertisers. So again, we have a lot of tools in our toolkit for addressing situations like this. We can use something like double ML or some version of inverse propensity weighting, where we model selection into receiving a sales pitch as a function of observable characteristics of a client and try to underweight advertisers that tend to have characteristics of receiving high sales pitches and overweight advertisers that have the opposite. Again, this will get us a causal answer through double ML, and we can try to use that in our decision making. Or if we're lucky enough to run an RCT, we can actually run an experiment where we pitch to a random subset of our clients and hold out another random subset, and again try to learn the counterfactual of what would have happened without the sales pitch from those in the holdout group. Now, by now, hopefully, you are actually convinced that, like in a lot of business scenarios, what we need to learn is not associations, but counterfactuals to make decisions. And we have a lot in our toolkit as seasoned practitioners to build those counterfactuals through some kind of a modeling approach. We can do synthetic controls, double ML, RDDs, instrumental variables. We can run experiments. And I want to argue that this is not where our job as practitioners is done. The real part of the job begins after we hit run on the model or run an experiment. And applying a causal inference algorithm or a model does not guarantee that we will get a causal answer, nor does an experiment guarantee that our answer is the actual causal answer we're looking for. Now, going back to some of our examples we talked about, I briefly talked over this where we said we can run a synthetic control model to construct a counterfactual of what would have happened without a marketing campaign. Now, again, the job is not done when we run the synthetic control model and report the point estimates and the standard errors. We need to ask the question of what do we need to believe about the data for the answer we provide to be the causal answer we were seeking. There are many reasons why a synthetic control model can go wrong, and I'm sure you can come up with many scenarios, but here, let's suppose we were treating a particularly big city like New York City, and our other control cities were relatively small cities, and we were trying to construct a counterfactual, but can we really construct a credible counterfactual based on all those other smaller cities to capture what New York's sales numbers would look like? Now, you might be thinking, surely if we run an experiment, we're probably good. suppose we ran a marketing RCT and we took 10 different cities, randomly put 5 of them into the treated group and 5 of them into the control group, and we ran our marketing campaign in the treated ones, and we're learning the counterfactual from the control ones. This is an RCT. It's the gold standard in causal inference. Is our job done now? And I think you will agree that no, our job is not done, and the world is not stable, and there are many things outside of our control. And even with an RCT, you need to make assumptions about the data generating process, and there are things you need to believe about the world for your answer from the RCT to be the causal answer you are seeking. Again, in this example, suppose we were running our marketing RCT and our competitor was also running a campaign in some of our control cities. You can see how things can go wrong even with an RCT, and there are many, many examples where this kind of things happens and we don't recognize it because we don't dig into our data and we don't talk to our stakeholders. Going back to the sales effectiveness example, suppose we ran a double ML model using advertiser characteristics to model our propensities and get an answer. Again, we're not done there, and we need to ask, what do we need to believe? Do we have overlap in the data? Can we construct credible counterfactuals from advertisers that were not pitched to understand what would have happened to those that were pitched? And are they comparable to each other? Do they share any characteristics? And probably there are factors we don't observe about who our salespeople talk to and how they decide to spend their time. And we cannot capture everything in our propensity modeling. And this is where things can go wrong. And this is where we need to, again, keep talking to our stakeholders, our domain experts, to evaluate our assumptions and what we need to believe about our models. Again, you might be thinking, we can just run an experiment. And maybe we are lucky enough to run an experiment and we've convinced our leadership that it's worth the cost. We are holding out a subset of our clients that we're not pitching to them, and we're pitching to a random subset of our clients. And we can get an answer from an RCT, but again, our job is not done, and there are many ways how an RCT like this can go wrong. What if our customers are talking to each other? And what if some of our customers in the treated group are talking to their friends in the control group? Again, an RCT does not guarantee that we get a causal answer, and we have assumptions we need to make about the world and evaluate them in order to ensure our stakeholders, our decision makers, that they can trust the numbers we provide them. The message I want to leave you with today is that causality is not a property of the data or the model or the algorithm we pick. It is a result of our beliefs and assumptions on the world. And no algorithm or method can guarantee that the answer we get are causal answers. That is a function of our beliefs and assumptions on the world. And when we're using these abundance of causal tools and techniques as practitioners, I want to reiterate that the real job begins after we click run on our causal inference algorithm and get the answers. And we should not stop by just reporting the point estimate and some version of a p-value or a standard error or a Bayesian credible interval. We need to assess the credibility of what we need to believe to get a causal answer, and that is where the real job begins. And that is all I have for you today. I'll be happy to take any questions if you have any.
So a question did come through. Is causality in an RCT more likely to be guaranteed with a large sample size because of the central limit theorem?
I don't think I can connect it to the central limit theorem, but under certain scenarios, it is easier to believe the assumptions you need to believe for an RCT to go through. You could be in a world where you don't need to worry about spillovers between subjects, and with a large sample size, you might have credible intervals or confidence intervals that are tight enough, and you can run sensitivity analyses to violations of some of your assumptions, and you can say, even in a worst case scenario where my assumptions are violated to a certain extent, our answer will still go through. And this is the kind of thing that I love to do. Rosenbaum-style sensitivity analyses, I think, is a very useful tool. And I think sometimes it's easier to achieve that with RCTs for sure. Yeah.
Brilliant. Thank you. That was all the questions. So you sorted. Got off lightly.
Thank you.
Thank you.
Thank you, Eray. The next speech we have is Maksim, CTO and co-founder of causaLens, who will be discussing some very exciting breakthroughs we're seeing at causaLens on the synergies between large language models and causal AI. Welcome, Max.
Thank you very much. Thank you very much for the time today, and thank you for the great conversations we've had all day. So today, I'd like to tell you about how we think about the way in which large language models and causality interface, and we'll also, in the meantime, touch upon the academic work in this field as well. But we'll also give you our own way in which we think about this. So we'll talk about the synergies in a broad sense, and how to think about large language models, and then 3 very specific kind of integration points between large language models and causal AI, around grounding large language models with causal AI, building large language models more effectively, and using them to extract causal domain knowledge. So, in the past few years, in the past, say, 2 years, there's been a huge onslaught of interesting research papers where people have gotten quite excited about large language models and started to explore this question. And there's so there's some great papers, and there is also this terrific comprehensive survey as well, which kind of gives a lovely kind of a tree of all of these interaction points. And what I like about this paper is that it gives these causal for LLMs and LLMs for causal kind of trees, right? So in other words, one is showing how causality can improve large language models and make them more, better at reasoning, better at explainability, fairness, and so on. And the other is about how can we use large language models to improve the way in which we develop causal AI. So today I'd like to focus on sort of specific business use cases and ways in which we can really apply this synergy, right, to make the life of our customers better, right? And so the way we think about it is like this. We think about the creation of causal models. So fundamentally, we care about the speed and productivity at which people go from data to decisions. And part of that process is creating causal models, creating causal graphs, and things like that. So you can leverage large language models to make that creation process better and faster. And I'll talk a little bit about how to use large language models for domain knowledge extraction, or how to use agents to help you build models more quickly, select methods more quickly, write code for you, things like that. Once you've built all of these, call them causal artifacts, then you can also use large language models to help your users or your business users or maybe your stakeholders actually utilize those causal artifacts and understand them. And so that's the consumption phase, and it's about getting trustworthy, causally backed decisions from large language models. So it's worth understanding a little bit large language models in a more broader sense. So let's take a kind of an information retrieval perspective on this, okay? So think about large language models as having some knowledge. That's this bit on the left, the knowledge base. Some method of extracting that knowledge from the knowledge base. That's the retrieval phase. And way in which they generate the answer. That's the generation there. So if you think about just plain kind of large language models, their knowledge base is essentially, they're generally trained on the entirety of the internet. So their knowledge base is in effect a distillation of the internet, right? And I think that's very important because that implies that whatever information they retrieve from their knowledge base, it is essentially stuff that they kind of read on the internet, right? Not, for instance, our own questions about our own proprietary data or something like that, right? It's going to be stuff from the internet. And the way in which they retrieve this data is quite inscrutable, right? We don't know precisely how they retrieve this data. And as a result, we know that LLMs have this interesting, exciting, emergent kind of a quote reasoning capability. But we do know also as a fact, and there's academic papers that talk about this, that this emergent reasoning capability of large language models is not fully developed, right? In specific terms, large language models, talk causality, but don't really understand causality fundamentally. And even after things where you fine-tune large language models and try to really make them better at understanding causality, they fail to fully comprehend it and fail to generalize to new causality problems. So how do we improve really upon this situation? And so the answer is firstly through this idea of grounding large language models with causality. So let me tell you a little bit about that first. So as we said, LLMs struggle with this understanding. They also struggle with quantitative reasoning as well. And so we want to answer questions about how, we want to make large language models be able to answer complex questions such as, they're potentially counterfactual, that need counterfactual calculations or interventional kind of calculations, right? For instance, this is an example of a question. And this is a problem that has been studied academically, and I'll tell you about the approach that we are taking to doing it. So our approach is the following. We want to have a number of causal artifacts. These could be causal graphs, causal models. Ideally, you can imagine a set of relevant causal models, all existing in your environment, in your organization, and you want to have them backing your agent that you're conversing with. Okay, so what you see here is a model which is a rung 3 level model, so it's capable of generating interventions and counterfactuals, and you can add it to an agent and as a sort of an API call. And then from that point onwards, this agent is modified in a way to query this model and to ask it for questions. And it can ask these rung 2 and rung 3 questions. In other words, interventional questions as well as counterfactual questions. So from a developer experience perspective, we think about it as, look, you have an agent and you can add these causal models and you can have multiple of them. And in that way, you have something that you can ask about questions, that kind of go across different models, right, in your organization. So for instance, and what is cool about that, if you remember, this is actually not inscrutable. This now actually provides ability to ground its statements in sort of citable information. So for instance, you can say, look, based on this causal graph, I have calculated the parents of this variable, and I now understand what are the driving factors influencing this variable. Or moreover, I can have more complex questions where I'm actually now applying an intervention, right, and calculating some kind of a difference between different analyses and giving that answer to the user. So this should help democratize access to understanding of causal models to all the users in your enterprise, right? So if we now go back to our information retrieval perspective, in effect, we've replaced the knowledge base with from this distillation of the internet to something that's very specific, right? A set of causal artifacts that we control, and we know exactly what we can put there. And the retrieval, the way it works right now is through this methodology of function or tool calling that is supported by many large language models. And what is cool about the generation is that it is actually transparent for us. So we now get citations, that we can actually verify ourselves. So we can trust the results that come out of the large language model. And what we find, for instance, is that there are still struggles and difficulties, by the way. For instance, you will find that it is hard for large language models still, or to get them to fully appreciate the differences between, say, intervention and a counterfactual. And depending on the size of the models or the eras of the models, they are sometimes quite good at synthesizing things, but sometimes they might not be able to properly cite information, or they may hallucinate. So now let's change gears and talk about how do we accelerate the rate at which we build causal models. So here is how we think about it. We think about, like I said, our objective is to go from data to decisions as quickly as we can. And so to this end, we build an agent that can get as its input modalities some kinds of questions and code. For instance, here is some code I'm writing to build some kind of a causal model. Can you help me with it, right? Moreover, I can pass that causal model into the agent, or say a causal graph or something like that, and even some data, right? And that agent is aware of the kind of the work that I'm doing. And then it also, leveraging all of our code, all of our documentation, all of our worked out use cases, it has the ability to look over that code, over that data, and to produce some outputs, right? So it can write code for us, it can build new causal artifacts for us, or it can even build user interface for say, business users. So you should be able to say, well, look, given the causal graph that I have and a model, can you please build me an application that lets a business user do certain interventions on that data, do some scenarios, what-if analyses, that kind of thing. And so here's some examples of how it looks like. So for instance, you can ask it to create a causal graph of a certain form. You can ask it to create some kind of a transformer that normalizes the variables within that thing, to create a structural causal model out of that. And what is very cool is that we have many, many worked out examples for this. We have a full code base that we feed into the agent, essentially. That gives it a lot of ability to solve these problems full stack, right? So from building a model to building an application for us, so that we can accelerate this journey. And here, this is an active area of research, right? So we haven't figured it all out, and so we have a strategy to how to go about doing this. We build agents that begin in a kind of a specialized part of the product, right? And then over time, we expect that they will become more capable and more complex, and a single agent will be able to take you through the whole process. But to first order, we think about more kind of like specific examples. Help me build a model, maybe that's one agent. Help me build an application, maybe that could be a separate agent, right? Because it uses potentially different techniques. And again, from an information retrieval perspective, how this works is that, well, now, in addition to causal artifacts, we are now providing to our agent the entirety of our software packages, the structure of them, information about each class, each function, each method, all of that, as well as worked out use cases across many different industries that we have in our product. And we use a variety of techniques here that I won't go into in detail, but you can feel free to ask questions. And we leverage the ability of large language models to understand and write Python code and put things together. Finally, we also help users extract domain knowledge from using large language models. This is really valuable, and it's actually something that people have looked at quite a lot. So there are papers that have looked at various algorithms to say use large language models to say discover causal graphs, or to extract causal relationships potentially from text, from domain knowledge. we try to do exactly the same in our product and to make it easier for our users to do it. So for instance, we can use large language models to extract domain knowledge from text or from the knowledge of the large language model has from this distillation of the internet, right? You can ask it to propose latent variables in your graph, things that you maybe haven't thought of before, things like that. The advantage of this is because we leverage domain knowledge in causalens quite a lot, right? Causality is, causal discovery, for instance, is improved a great deal by using human domain knowledge. And what's really nice is that you can actually just say things like this. You can ask, for instance, a large language model, given a set of variables, a data set, tell me some form of domain knowledge of for instance, which of these variables are exogenous, which of them I can't modify, and which ones I can potentially. So that's a form of a tier structure. So with kind of a one line of code, you can extract that sort of tier information, and then you can feed it into a quantitative causal discovery algorithm. So for instance, FCI. And so with kind of like one click of a button, now you're running a well-understood, trustworthy algorithm, but you're leveraging this domain knowledge that you extracted using the large language model. So again, back to our information retrieval perspective, here the knowledge base is this domain knowledge in the large language model, but it could also be a collection of internal text documents, right? So there's a lot of causal knowledge we find, embedded in organizations in text, right? And once you retrieve that knowledge, you can now create, you can extract this knowledge and like I said, use quantitative techniques to build causal graphs and structural causal models, which is really cool. So that concludes my talk. Thank you very much. I'm happy to answer any questions.
There were a few questions.
Okay, great.
So it's good. First one, how do you ensure your causal agent can't hallucinate? I'm sure that being based on causal model helps, but is there anything preventing it from making things up?
Yeah, absolutely. So if you remember, there was this notion of citations that the agent provides, right? So when you get an output from this causal model, you can simply see the citation that you get out of it, and you can track it and see the code that went into it, the analysis that went behind that point, right, that the LLM is making. So fundamentally, that's the way you do it. Yeah.
And different question. Given that RAGs retrieve relevant context through similarity, generally distance, how is the appropriate causal artifact identified for the query, particularly in cases with many similar causal artifacts?
That's a terrific question. Thanks for that. I don't think that necessarily one needs to use semantic similarity, right? I think the state of the art is to combine various techniques of identifying the relevant thing to query, right? So semantic similarity is around these embeddings that so you're looking for an artifact by looking for a kind of a semantic embedding of maybe a sentence of text or something in a vector database, right? But that's not the only way you can do it, right? You can provide a way for a user to provide some relevant keywords, for instance. You can do keyword search or things like that. And so it's a combination of these that's I think, state of the art.
All right, I'm going to go one more that's on the top of the list here. How can we make sure that the knowledge distilled from the LLM is reliable? Because the outputs from LLM sometimes give nonsense outputs.
Yeah, absolutely. So this is why I think you want to, once again, ground this in some kind of a documentation or something like that, right? So don't rely necessarily on fully this knowledge embedded within the large language model itself, but ground it based on content of text. And then you can, once again, you can actually refer to relevant facts from the text that say support a certain causal hypothesis. So we're saying that X causes Y because we see that information in these documents, for instance, in your database. Okay, thank you.
Thank you, Max. It's very exciting to see these two amazing technologies working side by side and making each other even greater. Okay, so next up, we are taking another 30-minute breather to recharge. So we'll be back, I think, around 4 p.m. for our final few sessions. And remember to pay a visit to the demo room if you haven't already. So our final I think scheduled demos of the day is profit scenario modeling. And if you didn't manage to catch the LLMs demo during lunchtime, you can obviously put in a request for Ronald as well to do the LLMs demo for you as well in the demo room. See you in 30 minutes. So please scan and fill out the quick survey to let us know how you found today. Okay, so next up we have a highly anticipated session. So let's welcome Guido Imbens, economics professor, Nobel Prize winner from Stanford University, who will discuss the implications of interference for running experiments and observational studies. Welcome.
Thanks. Thanks very much. Thanks for the very kind introduction. Thanks for the invitation to present here today. I was at this conference last year. It was a lot of fun then, and it seems like the crowd is even bigger now. So it seems to be going extremely well. So what I want to talk about today is about some problems, some of which I've been working on, kind of trying to deal with interference, kind of both in randomized experiments, where as a result of the interference, the experiments become much more complex in terms of the experimental design, and as well as in observational studies, where in the end most of the data we're going to be analyzing are going to come from. So what I want to do is first talk a little bit in general about interference or spillovers or interactions between units, kind of the complications that make standard randomized experiments, standard A/B tests, not effective for the kind of questions we're typically interested in answering, and then look at a couple of different approaches for dealing with particular types of interference or spillovers. And kind of in contrast to kind of other settings, in contrast to settings where there are no spillovers, where there's no interference, the designs and the analysis are going to be much more specialized to the particular situation. We're going to need to put some structure on the interference in order to deal with that. And often particular problems come with very specific types of interference that have a fair amount of structure that are going to be useful for trying to figure out what are effective designs. But actually, kind of to back up a little bit, about 6 years ago, I think 2018, I was at this conference. In fact, actually, this was a sort of very Silicon Valley experience. I was flying back from Seattle. I spent a day working with some people at Amazon, and the flight from Seattle back to San Francisco kind of always has a lot of people working in the tech companies. And so I ran into Ronnie Kohavi, who had been running experimentation at Amazon and at Microsoft for a while. And he told me that 2 days later, he was actually organizing this conference on experimentation. And he said, "Oh, it would actually be great if you could come along." I said, sure, I'll come along. And then 2 days later was this conference. And at the first slide, when they introduced the conference, said, "Well, we'll list the participants." But then it turned out I was the only one who didn't actually have any affiliation there with any of the tech companies. So I found myself in very interesting company there. But in that conference, kind of the theme was what were challenges in doing online experimentation. And two of the main challenges that were discussed there was one, the complication that typically we're interested in long-term effects of interventions, but we typically want to get the answers quickly. And so we may be interested if we change something in the experience for users on a platform, how's that going to affect their long-term engagement with the platform? But we want to make the decisions very quickly. There's no point in waiting 5 years because at that point the decision will be irrelevant. So we need to make a decision fairly soon. But then if we don't actually see the long-term outcomes, how are we going to make those decisions? And so last year at the causaLens conference, I talked about some of the methods dealing with it, trying to figure out what are good short-term measures and how you can combine different types of short-term measures in combination with observational data that link these short-term measures, these surrogates, to long-term outcomes as a way of trying to make principled and coherent, have a coherent way of making decisions in settings where we do experimentation, we do experiments, but we don't directly see the long-term outcomes we're actually interested in. But today, what I want to talk about is one of the other challenges that was discussed there at that conference: problems dealing with interference, spillovers, or interactions between units. And here a quote again from the paper that came out of that conference. Network interactions are a significant concern in A/B testing. And in fact, these type of complications are very common, are very prevalent in many of these settings. And they can be of different types. One is that the behavior of one particular individual may directly affect the behavior of those around them. And a long time ago, I think in 2014, there were some experiments done at Facebook on voting behavior. I think the particular intervention was that they set up a button on people's homepage that would allow them to signal that they had voted. And the question was kind of what I would do for the voting behavior of the individuals who were in the treatment group who had that button, whether they were voting more or less. But in addition, there was a question whether that would affect the friends of the people who were in the treatment group. Because if I am in the treatment group and I voted and I signaled that on my Facebook page, that would be seen by my friends, and they may then in turn also be encouraged, incentivized to vote, and if it may in fact also influence their friends. And so there was this was a very large scale experiment, I think, involving tens of millions of individuals, and there was evidence that certainly it affected the individuals in the treatment group, it affected their friends, and there was even some evidence that it cascaded further, that it affected the friends of the friends of the people who were actually in the treatment group. Another example that received a lot of attention is in this work, in this paper by Christakis, Fowler, and others, which was an observational study where they looked at the changes in weight among a number of individuals in Framingham, Massachusetts, and they found that changes in weight for individuals was associated with changes in weight among their friends, kind of both family and non-familial friends. And they argued, and they kind of did a lot of analysis suggesting that these associations were actually causal, that if we somehow affect the behavior of a particular individual in a way that it changes their weight, that would have a cascading effect on their friends, their neighbors, their relatives, and change their weight in the same direction. So that's one type of interactions that we may be interested in when we're trying to analyze causal effects. It would affect the optimal policies. If we know that what we do to one individual may affect the people around them, if we find that there are such indirect effects, we may focus the interventions on people who are particularly central in a network. We have a lot of friends in a way that it would maximize the impact of the intervention. But there's other types of interactions as well, and one type that I've been looking at in more detail recently is kind of interactions in marketplaces, and there the interactions are a very different type. They don't actually require people to directly be connected to other individuals, but these interactions work through markets. But I got here this afternoon. I took an Uber from Palo Alto, and as soon as I I take an Uber, it means that the driver from that particular car is going to be off the market for however long it takes me to get here. And that means that has a negative effect on everybody else who might want to get a ride somewhere. There's one driver fewer available at that point to take someone somewhere. And if there's a lot of people taking an Uber or Lyft at a particular point in time, that affects all the other people in the market. Similarly, or kind of differently, but in a similar type of market interaction, if I'm shopping, if I'm shopping online, if the marketplace changes the properties of some of the items, maybe gives a discount or maybe gives a fast shipping option on some of the items, that may affect the demand for other items that are not affected by, that are not directly exposed to the same intervention, that don't get the same shipping offer or a discount, because I might just switch from one item in the control group to an item in the treatment group. If a company discounts particular types of USB memory sticks, it's unlikely I'm going to be buying more memory sticks, but I may switch from the regular USB sticks to the discounted USB sticks. So in all these cases, there's interactions between these units, there's spillovers. And so if I just do a simple A/B test where I put some units in a treatment group and some units in a control group, and then compare average outcomes for these two groups, I'm not going to get an estimate of what would be the causal effect of switching everybody from the control group to the treatment group. And it is that type of setting that I'm interested in here, and trying to understand how we can do experiments, how we can analyze observational data in a way that doesn't give us answers to the questions we're actually interested in. And so, kind of at a general level, if we take the potential outcome perspective, as I saw my book with Tom Rubin was lying there in the hallway. So the way we set things up there for the case without interference is we think of there being for each unit two potential outcomes. One outcome that you would see that would be realized if the unit was in the control group, and one outcome that would be realized if the unit was in the treatment group. And what we're interested in is the average difference between these two potential outcomes, the average causal effect of some intervention. That would be a natural object of interest if the question is whether we should expose all units to that treatment or expose none of the units to the treatment. Now, in the case where there's interference, in principle, the outcome for one particular unit may depend on the entire vector of assignments for all the units. And that's going to make it very hard. Now, we might still be interested in what would happen if everybody was exposed versus nobody was exposed, but we're not going to be able to see or directly get a handle on both these items, because there's too many potential outcomes to be able to estimate that average difference. And so what we're going to need to do is put some structure on the interference, put some limitations on what how the interference occurs, how the spillovers arise. And that structure is going to be very context specific. In online settings, the particular rules of the platform may often determine the nature of the interference. So in the Uber case or the Lyft case, what I do in terms of taking an Uber or Lyft doesn't depend on what particular other individuals do. It just depends on the overall demand. It depends on how how many drivers are still available, but it doesn't actually depend on the identity of the other customers, of the other riders. In other cases, the interference may be related to a network, kind of in the Facebook experiment I described, whether I voted wouldn't directly affect anyone else unless they were in my network and they could see what I put on my Facebook page. And so in all these cases, the nature of the interference is going to be potentially very different. And trying to figure out what are good working models for dealing with for modeling the interference is an ongoing area, and it's a particularly interesting area because it's a very interdisciplinary field. There's a lot of participation from computer scientists, from social scientists, kind of thinking about how individuals behave and make decisions. There's a lot of statistics expertise required, and there's going to be a lot of interesting roles for AI to kind of help uncover the dependent structure in rich data sets. So now let me kind of talk about some of the specific methods that people have tried to use to deal with some of the types of interference. And one method that has a fairly long history is thinking about is using clustering methods. So we may have this population of units, but it may be that there's some partition of that population such that the interference is limited to within the clusters rather than across the clusters. And so in an educational setting, that's a very common approach, where we may think that exposing individual students to an intervention may affect other students, but it's not necessarily going to affect all the other students. It's just going to affect the other students in the same classroom or in the same school. And so if instead of doing a randomized experiment where we randomize the students, if instead we randomize the schools or the classrooms, we may be able to get rid of the interference and analyze the data at the more aggregate level, at the classroom level, at the community level, at the family level. And then we can use this data at that more aggregate level using the standard methods. Now, the challenge is that that this is all good and well, if we actually know the clusters, if we know how to partition the population in such a way that the spillovers are limited to within these subpopulations, within these clusters, but not across clusters. But often we don't really know exactly what that clustering structure looks like. And now we have a problem. We need to kind of use the data to figure out the clustering structure at the same time we're trying to analyze these data and figure out what the effects are. And we may have some information on which units are closer to each other and which are further apart, where the interference or the spillovers are more limited, but we may not know exactly where to draw the boundaries for these subpopulations. And so this is the type of thing that's often been used at Facebook. Of course, there's in the end one big graph that connects pretty much everybody in every Facebook customer. And so we can't find clusters such that these clusters are completely separate, that there's no connections between these clusters. But we can try to cut the overall graph in a way that is a relatively small number of cross-cluster connections so that we limit the amount of spillovers that would be biasing comparisons between the clusters. In other settings, say in a supermarket or in an online shopping platform, we may again want to cluster the products in a way that that spillovers are mainly contained within these clusters rather than across the clusters, but it's again not clear exactly how to do that. Should a cluster be all dairy products? Should it just be different types of milk? Or should it be one type of milk in different sizes? There's probably fewer spillovers to different types of milk and even fewer to non-dairy milk or other dairy products, but there may still be some spillovers there. And there's going to be a trade-off between the bias that we get from making the clusters too small to the lack of precision that would come from making the clusters too big. And some of the work I've done with Davide Viviano and some people at Facebook kind of looks at optimal ways of clustering in settings where we don't really know exactly what the nature of the connections is, but we have some sense on which connections are stronger than others. Another type of experimental design that tries to deal with online marketplaces was explored in work by a student of mine, Evan Monroe, and two colleagues of mine at the Stanford Business School, Stefan Wager and Kwang Su, who look at a setting where the interference is mediated by prices. So intervening on a particular individual may have some effect on their demand for the particular product. And if a lot of individuals are assigned to the treatment, that may increase demand for the particular product. And as a result, prices may increase to reflect the increase in demand. And what Monroe, Wager, and Su are interested in is trying to disentangle the direct effects of these interventions from the indirect effects coming from the change in prices as the result of the intervention. And so what they do is perturb prices for every individual a little bit, changing a little bit the price paid by the customers and received by the sellers in a way that allows them to disentangle the direct effects of the intervention from the indirect effect on the equilibrium prices that come from changing the experience for a substantial number of units. The third case I want to look at, and this is one I spent a fair amount of time on recently, I'll refer to as multiple randomization designs, and this is in joint work with Pat Byery and a couple of other researchers at Amazon. And at that work, we consider settings where we have multiple populations that are interacting. And so the type of examples we have in mind there are at a shopping site, we would have buyers and sellers. At Netflix, you would have movies and viewers. At Airbnb or VRBO, you would have rental properties and renters. And at Lyft or Uber or other rideshare companies, you would have drivers and riders. And the key thing is that in some of these settings, we could assign the treatment at the level of the pair, movie viewer or buyer seller or property renter or driver rider. For example, in the rental property renter case, you could imagine that VRBO could show more information about a particular property to some of the potential renters. So if a particular individual goes to the website, looks at a particular property, they may see more information in terms of more pictures, more videos, more reviews of that particular property. But another potential renter may not see all that information. And at the same time, the same individual may see that information for some every possible combination of treatment control, the entries in that matrix is a possible experimental design. And now, kind of, if you think of a standard A/B test, we could do a movie experiment where we would randomly assign the movies to the treatment group and the control group, and every viewer sees the same thing for each movie. So every movie is either in the control group or the treatment group, and every customer would have the same experience for that movie. Or we could do a viewer experiment where we randomize the viewers, and every viewer has the exact same experience. Every individual viewer has the same experience for all movies. So those would be two ways of doing a standard A/B test. But once you set it up this way, where the assignment is a matrix, you can imagine doing a richer design where you randomly pick some movie viewer pairs and assign them to the treatment group. And now the key insight is that now we have a richer experiment where we can learn both about the direct effects of the intervention and the indirect effects coming from some viewers having different experiences for different movies. And so if one of the concerns is that the treatment may make customers switch from one product, from one movie to another product, we would be able to detect that during this type of experiment. For example, if we compare viewers who are sometimes in the treatment group and sometimes in the control group, that is viewers 5, 6, 7, and 8, and we compare them with viewers who are always in the control group for the same set of movies. So if we do that for movies 1 and 2, comparing the red Cs and the blue Cs would tell us something about the cannibalization, about the effect that customers would switch from treated products to control products or the other way around. And similarly, if we compared the green Cs and the red Cs, we would see something about the indirect effects coming from the way the movies are advertised changing in response to the treatment. And so in the end, if we look at all the possible combinations, we can try to estimate the total effect by comparing the treated pairs to the red Cs, which are movies viewers that are always in the control group, and we can look at various types of indirect effects, or we could look at the direct effect, where we take this double difference to partial out the indirect effects. And so what this illustrates is that this type of experiment is going to give us much richer answers to what is happening in the world, what the overall effect would be, what the direct and indirect effects would be of these interventions in settings where there's potential spillovers. Now, you can make these multiple randomization designs much more complex. So here is an example of a design where you would split the viewers into two groups. One set of viewers would be exposed to a movie experiment where we randomize the movies. The other viewers would be exposed to a viewer experiment where we randomize the viewers. And now we have a whole bunch of different control groups, movie viewer pairs that are exposed to the control treatment that have different overall experiences and that are going to allow us to disentangle the equilibrium effects from the direct and total effects. And similarly, we can compare different types of treated movie viewer pairs in a way that would allow us to learn about both direct and indirect effects. And these designs are now actually being used in some of these online settings where there's concern about interventions and where it's important to get both the total effects as well as the indirect effects. Last example I want to talk about is another very recent set of experimental designs referred to as bipartite experiments. And so here the setting is again one where we have two different populations. We have a set of units that I'll refer to as intervention units that we can choose to either expose to an intervention or not. And in one of the early papers in this literature by Ziegler and Papageorgiou, those are power plants that could be either given a pollution abatement system or not. So the treatment here is putting something in these power plants that's going to reduce the pollution they put out. Now, we don't directly care about how much pollution they put out. We're interested in how that affects the health of the individuals in the surrounding communities. And so the outcome units here are communities nearby these plants. and where we measure some aggregate indicators of health of these communities. In fact, in this particular paper, this was measured at hospitals, how many people would come in with respiratory illnesses. But particular hospitals could be affected by multiple power plants. There were a whole bunch of power plants. Each power plant may affect a whole bunch of communities depending on the prevailing winds and the area these power plants were in. And so there's a number of units. There's capital J power plants. There's capital N hospitals. Each hospital is potentially affected by a number of the power plants. And we're interested in what would happen if we introduced more of these pollution abatement measures that would clean up the air for some of these power plants, but not necessarily all of them. And so the way I want to think about it in a graphical version is that we have these two sets of units, these intervention units. Each intervention unit may affect some of the outcome units. So intervention unit A, power plant A, affects hospitals 1, 2, 3. Power plant B affects hospitals 3 and 4. And power plant C affects hospitals 3, 4, and 5. And we're trying to figure out what the causal effect would be of cleaning up all these power plants or some additional power plants, given data on health outcomes for these hospitals and the treatments for these different power plants. And again, like these multiple randomization designs, we're now in a much more complex situation. We're doing experiments and figuring out how to learn from experiments what the average effect of the intervention is going to be much more challenging. And even designing experiments that tell us what the effect is going to be a much harder task in this setting. Now, some of the examples where this comes up, and I mentioned the Ziegler-Papageorgiou work, where they look at the effect of power plants on health outcomes. A much earlier paper that kind of used another set of methods, but it really fits in much more naturally in this setting, was one by Jim Stock at Harvard, where he was interested in the effect of cleaning up the pollution sites, and the outcome units were houses, and he was interested in the effect of cleaning up these pollution sites on housing prices, where some houses were close enough to be affected by multiple pollution sites, and we need to deal with this type of interference again. The third paper is a recent one by Kirill Borushak and Peter Hull, where they're looking at the causal effect of building railway lines on the economic development of regions, and where again the intervention units, the potential railway lines, may affect multiple regions that they're connecting that are close to these railway lines, but the outcomes are defined in terms of these regions, which again that may be affected by multiple railway lines. So I'm running out of time here, but what I hope that this illustrates is that in many settings, kind of the standard setup where we think of units as being completely separate, where we don't worry about interference, is often not justified. There's many settings where interference, where spillovers, where interactions between units are of the essence, and where they're intrinsic to the problem. In all these marketplaces, the key to their success is that they bring together these different populations, and that these populations interact with each other in systematic and strategic ways. And so dealing with the spillovers and the interference is going to be of first order importance there. And there's now a whole bunch of methods being developed that's going to help us do that more systematically in a way that does justice to the particular types of interference that arise in these specific settings, whether that's coming from networks or coming from marketplaces or from these bipartite graph structures. Thank you.
Thank you, Guido. We've got time for questions if you're happy to answer a few. Yeah. So they've been sent through, voted up. So the one that comes at the top question, regarding simple multiple randomization design, do you have concerns about splitting the market, changing the structure of the interference? So it may be fine for movie viewer pairs, but may be more concerning if it's for rideshare driver riders.
Yes. So in the driver rider, sort of in the Uber, the Lyft type of setting, it's clear that randomizing either drivers or riders is not a very effective way of learning about what the effect of intervention are. And so there, the way this type of experimentation is done is often through crossover designs, where in a particular, so where the entire market, say the entire US, is separated into a bunch of regions, into a bunch of sub-markets, where most of the interference is contained within these regions. Then just randomizing these regions is not going to work well enough, because there's not enough power, there's not enough of these regions to get precision. So what they then do in addition to that is switch the regions from treatment to control, kind of over the day or from one day to the next, sometimes kind of within the sort of every hour or every day or every week, in a way that allows you to kind of use each region, so each market as its own control part of the time. And so you do the randomization both across regions as well as across time. So you can think of that as a multiple randomization design, where one of the populations is days or hours, and the other population is markets. And now you randomize both in strategic ways to optimize the precision for the experiments.
Perfect, thank you. So slightly different question. Do you think it's possible to build a systematic framework or algorithm or agent to help address spillover effects in general?
Yeah, I think that's a very interesting question. Sort of, unlike some of the other settings where people have looked at causal inference problems where we essentially have no interference, there's a lot of ways of making the analysis systematic, where there's a lot of commonalities between the different models. Here, what is challenging is that the particular marketplaces or the particular platforms have specific rules that determine how the interactions take place. Sometimes it's not the fact that I'm in the treatment group that directly affects another individual, but it's only through my actions, through my outcomes, that I can affect other individuals. They may not see whether I'm in the treatment group or the control group, but they may see my actions, and that in itself affects them. In other cases, it's whether I'm exposed to the treatment or the control group that directly affects other individuals. So they're finding automatic ways of trying to kind of organize the types of interference would be incredibly helpful. And I think their large language models may well be able to help finding ways of systematizing that. And this is still fairly early in that literature, and trying to figure out what effective models are there. So I think we're going to need all the help we can get there.
Like that. I'm actually going to go straight into another question slightly related to the comment there you made on the large language models. So for all the mentioned types of experiment, the structure of the interference between units seems quite paramount. Do you think AI in general could be used to detect feasible structure between units in order to characterize these interference effects?
Yeah, I think that is potentially a very fruitful direction to look at. I think traditionally we've looked at very limited types of interference, because economists have traditionally paid a lot of attention to perfectly competitive markets, kind of where the interactions were very, very structured. It was only through prices. Prices were set through a market equilibrium. And that's kind of a very convenient way to kind of think about how these interactions take place. But that's clearly not what's happening in practice. There's a very nice PhD thesis many years ago from this woman, Katie Grady at Princeton, who actually went to the Fulton fish market and collected data on on sales for fish at that market, kind of between a particular trader and the customer, and then you actually see that it's not really one single price every day. The kind of price differed from one customer to the next, whether this was a regular customer or not, and what particular relationship the seller and the customer had. And so the interactions in the end are much more complex, and she collected this huge amount of incredibly rich data, and she did, and kind of I've worked with this data as well. We tend to kind of analyze this in a very structured way, but the richness doesn't really come out of that, and that's where these large language models can potentially help and figure out more systematic patterns in these interactions.
Brilliant, thank you. There are lots more questions, so what I might actually suggest is if you're happy to stay around on the networking drinks, then please do grab and ask your questions there. But otherwise, thank you. Thank you, Guillaume.
Thank you very much, Professor Imbens. So for our final session of the day, please welcome Sachin Raj, Principal of Data Science and Advanced Analytics at AT&T, who brings to us a talk on the synergies between predictive and causal models in customer churn reduction. Welcome.
Good evening. Ready for the last one? Many years ago, I learned that when you teach a child how to model trains, you most likely keep him out of poverty and weeds. But in the recent past, I have learned and observed that when you teach a child to train models, you not only make him the world's richest, but one who can smoke all its weeds. You are looking for a joke, I tried. It's difficult to convince data scientists, especially the last time. But anyway, very thrilled to truly share a few lessons I have learned over the years. My name is Sachin Raj. I work for AT&T as a practitioner of data science solutions for many of the business challenges we have. Moved around small biz, mid-sized area of work, then went to consumer, then returned to the enterprise unit, working under the marketing analytics. What I am going to talk about, you have seen these numbers, and if you haven't, you probably got dropped from another planet here. These have been independent numbers published by different institutions, but you put them together, something emerges. That the impact to market is literally less than 1%. AI has not stood up to its hype when it comes to market impact. We can all agree on this one, that all of the models, the analytics that we develop and deploy are around decisions. And those decisions are tightly tied with return on investments. What happened? There you go. So now why failure? Why that AI has not stood up to its hype? Some of us touched on some issues and challenges that we face in our organizations, right? And I think, I'm convinced on this, the most important challenges come from a lack of cohesiveness, a disconnect among these three things: models, model outcomes, and ROI. And if you go further deep inside, you will figure out, I would try to find a solution or find a problem and dive deeper and understand why. You will see these keep coming, that we keep using vanity metrics. Talk about accuracy rates. We talk about F1 scores. These can take us to a large degree, directionally. But by the end of the day, when it comes to returns, these do not have any assumptions that are baked into it. You will see these metrics don't have any connection with the actual business outcomes. For instance, and I'll touch on that. And then ultimately, we have methods and procedures for model development, structured thinking for everything. But then when it comes to stakeholdering, we have business partners, we have data scientist teams, that there isn't a framework, a cohesive structured thinking of how a problem is developed, stated, and taken to market or taken to production. What I'm going to propose is sort of a practical suggestions. A few lessons I learned over the years, that when I would see these issues, I would strive hard to figure out why. And some things that I have identified as 4 issues for which I have these 4 solutions. Things like, hey, if you do not have a KPI that ties with, or a business KPI that doesn't tie with your model outcome, engineer one, right? CLV, or rather, let's say churn modeling. We have a predictive outcomes that clearly gives us a propensity score. But then we look what? Volume. What is the connection? Almost nothing. Know, very important, that the value of insights are extremely important, or rather sometimes more important than your predictions. One of us gentlemen touched on, we have all these models, we take them to production, and nobody cares. Why? That's exactly the problem that I attempted to diagnose. And eventually, when I use these little ideas, or rather, in my view, causal thinking or the why thinking, not just for the model outcome, but start from even before developing the model. You start developing these early insights, and you work with your partners, and you will see some evidence of what I'm talking about. The third point. We guys all don't even think about the benefits of classification in terms of dollar value. But often overlooked even further, never even considered, even if you just think about benefits, is the cost of misclassification. You have no idea sometimes that a little change in the cost structure could completely destroy your model outcomes in terms of the lift that you produce. And the last point is take advantage of the power of persuasion, which means think about uplift modeling. Anything causal inference that brings to the table that eventually could produce much higher marketing returns. The first one, I've structured this as a problem that you would see, and there is sort of a recommendation and some evidence, and then we will track down to the solution itself. The 4 problems that I've identified are around this particular business problem, right? Predict churn, and also find why. 2 months ahead, 3 months ahead, figure out what churn. So it's a combination of predictive models and prescriptive models, causal inference, right? So I am assuming, based on all of the work that I've heard or listened to, we will have the coexistence of predictive machines coexisting with causal inference. So in this case, you have model, it's working well, right? You take them to market, but then about a month or two later, you want to find what my actual lift was. It had very high lift when you developed it. And now you see nobody knows. Not a single soul in your company knows. What's the point of developing a model if nobody can track it? Of course, it's sometimes complex. You have, channel attribution, very many complex channels running together, but you can trace it back down to a single reason that your model outcome does not tie with the KPI or the business KPI. CLV is a classic example. Think you can feed your model outcome directly into CLV. And CLV can attack many wide variety of predictive problems because it takes margins, takes a discount rate around risks, and then feed the churn propensity into it, and you get a pretty good outcome. But when you think like that, the solution again is right. If you don't have one, find out one. You're all mathematicians, statisticians. You can cook one, right? Develop one, engineer one. But the benefit of this is you think about looking at a more granular level, right? It forces you to consider the different cohorts of customers. Customers with higher retention rates bring larger value, unlike the lower ones. And so, marketing teams do have the ability to target different types of customers this way. Secondly, again, you have a great model. You roll out in production. Nobody cares. About a year later, you find out I had 200 models in production, 30 of them used. Why? So you track, you go to a stakeholders and find out you have these little processes that you look at the check marks. They all consider there's a check mark that this particular campaign really used a model, or rather, there's a check mark. Nobody knows what they used for. They just looked at it. They never used it. They didn't even log in to look at the scores. And long story short, you will find out things like, hey, look, my sales compensation is based on the number of calls I make. It means the first, second, third quintile or quartile or whatever that you develop from your list of million prospects, or in the case of churn, customers. Nobody cared because it only produced about 30,000. They wanted 300,000. And so you work hard all years. And how do you make a change? It is not a model problem. It is not anything else other than a company strategy problem. How do you influence strategy? How do you bring change? And I have found that you can move needle, that when you work very closely with your stakeholders, partners, by finding these early insights. This is a data set from Kaggle, right? And I put it out and you figure out that some of these customers have Simpson's paradox problem, some of these profiles, where you see the customer with a contract type who signed up for a month over month and a 2-year contract, both have long tails, but completely opposite behavior. Right? When you share this with your stakeholders, you create these aha moments. You create this trust. You partner with them very closely, and then you create an anchor in the culture where they trust your models. And slowly you start seeing the usage of the models go up. Nobody likely heard about half-time value, customer half-time value. You think about 50% of the customers, whoever signed for the 6-month contract, leave in about 6 months. Here, more than 50 stay for almost 6 years. These are valuable inputs where your stakeholders can take this information and develop your campaigns for the specific projects. Another problem, which is models were great. You took them to production, aha moments creator, but somewhere things got screwed up. Nobody knows why. There is big disappointment. And now you try to diagnose and you figure out what happened. It's a simple example from that same data set. That here is a model outcome, right? You have a classification matrix. You put together the number that is like about 80% accuracy. You have a cost of, cost of the what do you call? It's an average cost of, the false positives and false negatives. That you just keep in mind that costs are not they're not symmetric. That I simplified it just by taking this the symmetry cost. But keep at 130 and you barely made your case. Your model worked, right? But then with the same outcome, same 80% rate, your price or the cost improved or made it worse by a few cents. But from 130 to 2, you are underwater. So now you use some feature engineering, spend a lot of time, push about 100 from here to the other side, right? And all of a sudden your model accuracy rate went up to 85%. And then you feel pretty good. The same accuracy rate. Let's say your billing got screwed up. You became liable for something. You ended up spending money, paying back customers. You're completely underwater again. The point being this, that misclassification costs are very vital, very important for us to understand and dissect and think way ahead in terms of average costs that you put together in practice before you can really convince the stakeholders and ensure that they agree upon, they understand what the challenges are, what the underpinnings are before you take the model to production. Lastly, a similar problem, you have a high rate of success in terms of the model outputs as you developed it. But then you have about 14% of true positives. And you tell this to your stakeholders. The immediate understanding and expectations are something like, are we going to get 14% conversion? Something like that, right? It is quite naive, but you go about the campaigns, and then you end up having about 3%. Lift is just about 3%, which is darn good. In a randomized model, you just pick a random, leads, or in this case, customers, you will likely have about 1% at max, or much less than that. But this is providing much more lift. Then what happened was the complaints start pouring out, which is, hey, look, I had 14%, we ran a large campaign. Think about it, we run at large scale. It's millions. And then every time you spend $1 or $2 for a promotion cost, for an email that you sent out, it adds up. And so we run these large campaigns, and they simply come back to haunt you where you wasted a lot of money in marketing spend. And the question is, can we just target the persuadables? Practically, that is where the next steps would be, where we can be prudent in using an uplift model, understand ACMs, and more about, think about these ACMs as some things that can contribute to stakeholdering and building the trust early on as I suggested, to provide early insights to the stakeholders as you model through. So this is some of the lessons I learned, and it comes down to thinking about a couple of key points. One is, I often get called on to solve some complex problems. And it, goes about the thinking, right? Can we add more data? The lesson I've learned is that there is a decremental or declining value for adding more data. At some point in time, it's not. You can add as much as you want, but it all goes back to, playing some fundamental rules, going back to the basics, and think from the stakeholders' point of view. And equally important, as someone else pointed out, avoid these jargons, build the trust, and think from the dollar value point of view, and then you take it all to production. I think you will start moving the needles. Now, look, I think the few things that I wanted to suggest are things that I learned over the years. Now, are they going to move mountains? I don't think so. Are we out of the woods yet? No. If you think about what pundits would say the challenges are in the as a field, you would see some pointing out, we have this infrastructure issue and our models are failing or data is not good. If the data is good, then you talk about skills, and then if the skills are good, then you have MLOps problem. You go on, and then comes down to, okay, causality. Hey, look, there's all BS about correlation. Now we talk about causal thing. Okay, we got it. Now we come to this. Are we out of the woods? Well, look, I think it's a journey, as we pointed out. And if we, as practitioners, think causally, not from the model outcome alone, but as I mentioned, as a framework, as sort of power principles to keep in mind. Maybe you can add more than this or eliminate one of these, right? But think from that vantage point and put this into practice. I think we will start making or moving the needles. And so when we keep moving the needles, one here, one there, eventually I think we'll end up moving mountains. That's my story.
Thank you, Sanjay. Perfectly timed. Very impressive, very impressive. But I'll squeeze in one question for you. Can you give some examples of the vanity metrics you mentioned earlier?
Which?
The vanity metrics.
Accuracy rate is a vanity metrics. I would call it simply, it'll take you to some extent. F1 score is a vanity metric. There is no thing. Why am I calling it that way? Because accuracy rate can be inflated or deflated just by adjusting a threshold. Your stakeholder might be impressed by a 92% accuracy rate. You can figure it out. A clever data scientist can sit and squeeze a few adjustments there, and you can produce a 98% model accuracy rate. And that's why I call it as simple as that.
Thank you, Sachin, and what a great way to end the conference. So that is the final one of our lineup of amazing speakers, so I'm sure we will have our takeaways from today. So it's super encouraging to see the progress we've made as the Causal AI community, how technology leaders of today embracing Causal AI and seeing the value that embedding causal reasoning into AI brings to enterprise decision making. So today we've had great use cases, case studies from retail, government, marketing, healthcare, and sustainability. And also we heard about challenges and how enterprises can make their causal AI projects a success. We also saw the synergies between causal AI and other technologies and methods such as grounding LLMs with causal reasoning and working alongside predictive methods. And finally, we hope you enjoyed the demos given by Ronald in the demo room, and also the presentations by Darko, Max, and Tom from the causaLens team. And we hope to be a part of your causal AI journey going into the future. And it's an exciting time to be working in Causal AI. And that brings us to the end of the conference. Thank you so much to our amazing lineup of speakers for making this event such a success. And also thank you very much for the attendees, both in person and online. We hope to come back again next year and hear about all the amazing progresses that everyone's made here. So I'll wrap up here. So we have networking drinks in the lounge. So please do stay for that. And please remember to fill out your feedback cards so we can make this conference even better in the future. Thank you very much for having us today.